You're asleep, completely out, drooling on your pillow, probably snoring, zero awareness of the world around you. You are, by every biological definition, helpless. Now, imagine you're not in your bedroom. You're in a tent, a thin piece of nylon, like embarrassingly thin, separating you from a forest full of animals that could absolutely end you if they felt like it. Lions, bears, wolves, leopards, creatures that can hear your heartbeat from across a clearing, smell you from a mile away, and see perfectly in the dark while you're just lying there with your eyes closed. And yet, you wake up in the morning every single time. Why? Seriously, think about this for a second. A sleeping human is just meat, slow meat, quiet meat. Meat that can't fight back, can't run, can barely even register that something's happening until it's already happening. You'd think predators would be circling campsites every night like some kind of all-you-can-eat buffet, but they're not. They almost never are. And the reason they're not, it's not one thing. It's never just one thing. There are several layered explanations, each one more fascinating than the last, and together they paint this picture of a strange, invisible agreement between humans and the wild. An agreement that goes back further than civilization, further than agriculture, further than anything we normally think of as human history. This goes deep. Let's go. Start with the thing that sounds like an ego trip, but is actually just biology. You are terrifying. Not you specifically. You, right now, watching or reading this, are probably fine, normal, not particularly scary. But humans as a species, to predators, we are genuinely, deeply, evolutionarily frightening. Not in a way that's obvious from looking at us. We don't have claws, we're not fast, we're not particularly strong for our size. We can't even see well in the dark. On paper, we're kind of a disaster as an animal. And yet a study published in 2019 by researchers at UC Santa Cruz found something remarkable. They played audio recordings of human voices near mountain lions, also called pumas or cougars, in the Santa Cruz Mountains in California. Normal human voices, people just talking, and the pumas fled. They fled at the same rate they fled from the sound of dogs barking, and in many cases even faster. These are animals that take down full-grown deer like it's nothing. Animals that can drag a kill up a steep hill. Animals that are objectively absolute units of predatory efficiency. And they heard a podcast and ran. That wasn't a one-off result. The same research showed that pumas abandoned food they'd already killed, food they were in the process of eating when they heard human voices nearby. They left their meal on the ground and moved away from the sound. From a survival standpoint, that's an enormous cost. A predator giving up a kill is basically working for free. The calories burned to make that kill don't get replenished. And they still did it because the discomfort of being near humans outweighed the cost of hunger. That result confirmed something biologists had been noticing across multiple continents and multiple species for a long time. Lions in Africa's Kruger National Park reduced their movement in areas with higher human activity. Tigers in India give wide berths to villages even when those villages sit in the middle of prime habitat. Jaguars in the Amazon have adjusted their movement patterns to avoid locations where humans are regularly present. These aren't animals that are physically incapable of attacking. They're animals that have decided, at a species level, over thousands of generations, that being near us isn't worth it. And the reason for that is one of the most brutal facts in natural history. We have been hunting and killing large predators for so long and so effectively that we have literally shaped their genetics. Think about the scope of that. Humans have been active predators for somewhere around 2 million years. We hunted mammoths out of existence. We wiped megafauna off entire continents. Giant sloths, woolly rhinos, saber-toothed cats, cave bears. Species that had survived ice ages vanished within thousands of years of humans arriving in their territories. In North America, we hunted wolves to near extinction across the entire continental landmass. We eliminated mountain lions from the entire eastern half of the continent. We shot, trapped, and poisoned predators so systematically and for so long that the ones alive today are descended from the animals that were most careful around us. That's not a metaphor. That's natural selection. The lions that approached human camps too boldly got killed. The wolves that preyed on human settlements got hunted down. The predators that kept their distance, that treated humans as something to avoid rather than something to engage with, they survived. They reproduced. They passed that inherited caution to their offspring. Over thousands of years and thousands of generations, that caution became biological. It became instinct. It became the baseline behavior of every large predator that shares space with humans today. So, when a leopard picks up your scent in the night, somewhere deep in its nervous system, a very old alarm goes off. Not a thought, exactly. It's not sitting there consciously thinking about human history, but an ancient, wired-in, inherited signal that says, be careful around that thing, don't engage, move on. That alarm has been passed down from every ancestor of that leopard that survived a close encounter with humans. It's a biological memory, and it runs deep. Now, let's talk about your smell. You've probably never really thought about how you smell because you're surrounded by other humans all the time, and you've normalized it completely. But to a predator operating with a nose that's anywhere from 10 times to 100,000 times more sensitive than yours, depending on the species, you are broadcasting an enormous, detailed, and deeply strange chemical signal. Bears have a sense of smell estimated to be about 7 times stronger than a bloodhound's. Wolves can detect scents from nearly 2 miles away under the right conditions. Big cats have a specialized organ in the roof of their mouths, the Jacobson's organ, that essentially lets them taste the air and analyze chemical information at a level we can barely imagine. When these animals encounter a sleeping human, they are receiving a flood of olfactory data. And a lot of that data is just wrong. You smell wrong. You smell like synthetic fabrics like nylon and polyester and whatever chemicals were used in the manufacturing process. You smell like processed food, the meal you ate hours ago, the snacks in your bag. You smell like soap and shampoo and sunscreen and insect repellent. A cocktail of artificial compounds that has no analog anywhere in the natural world. Beneath all of that, underneath the layers of modern human life, you smell like a primate, which is something, but it's not the thing. Not the deer or the wildebeest or the rabbit that these predators have evolved over millions of years to recognize and hunt. A predator's hunting instinct is not generic. It's not a vague desire to kill things that moves. It's a finely tuned system calibrated to specific prey. A wolf's predatory response is triggered by the movement patterns of ungulates. A lion's strike mechanism is activated by the shape and speed and smell of animals it has hunted thousands of times. You don't fit the pattern. You're not in the system. You're an anomaly. Anomalies trigger caution rather than aggression in most predators. There's also the campfire effect, which is one of the most underrated things humans have ever figured out. Fire is one of the only stimuli that produces a near-universal fear response across virtually all land animals. It's not a learned behavior. It's not something animals figure out from experience. It's innate. It's ancient. Animals that were afraid of fire in the wild survived wildfires by running. Animals that weren't afraid of fire didn't. The fear is so deeply embedded that laboratory-raised animals who have never been near fire in their lives will show avoidance behavior at the smell of smoke. It goes that deep into the evolutionary code. Humans discovered fire somewhere between 1 and 2 million years ago, and for most of that time, sleeping next to a fire has been standard operating procedure. We weren't doing it just for warmth or to cook. We were doing it maybe without knowing it consciously because it works as a repellent. A campfire doesn't just keep you warm. It broadcasts a signal into the surrounding dark that says something dangerous is here, something that controls fire, something that should be avoided. The predators got that message, and they've been getting it for so long that the message doesn't even need to be decoded anymore. It just triggers avoidance automatically. You figured that out before you figured out farming, before you figured out pottery or writing or architecture. Fire first. Smart move, honestly. Now, let's tackle the biggest myth about predators, because movies have spent decades getting this completely wrong. Predators are not reckless. This is so important. The image of the apex predator as this fearless, unstoppable killing machine that attacks anything within range is fiction. Pure fiction. In reality, large predators are extraordinarily careful about what they engage with because they have to be. A lion doesn't have health insurance. A wolf doesn't have sick days. One serious injury, a broken leg, a deep bite wound, a damaged eye can mean a slow death by starvation. In the wild, injuries don't heal at the vet. They either heal on their own while the animal somehow still has to eat and hunt, or they don't heal and the animal dies. This means every single decision a predator makes about whether to engage with something is a survival calculation. Is the caloric value of this target worth the risk of injury? Is this prey item familiar enough that I know how it will behave? Is the chance of a successful hunt high enough to justify the energy expenditure? A sleeping human fails this calculation in multiple ways. First, unfamiliarity. A predator is most confident attacking prey it knows. It's watched the prey animal hundreds of times. It knows how a zebra runs, where its blind spots are, how it kicks when it panics. It does not know how a human will respond. Humans are wildly unpredictable. We might wake up screaming. We might have tools nearby. We might have other humans nearby who will respond. We might thrash in completely unexpected ways. For a predator trying to minimize risk, that level of uncertainty is a massive red flag. Second, the size question. Humans, when they stand up, are actually pretty big. We're tall, upright, and our bipedal posture, standing on two legs, makes us appear larger and more imposing than most prey animals of equivalent weight. Researchers studying predator-prey dynamics have noted that bipedalism is itself a kind of threat display. Standing upright is what gorillas do when they want to intimidate. It's what bears do when they want to look threatening. A creature that walks around like that all the time as its default mode reads as inherently assertive to other animals. Even asleep, the silhouette of a human shape is unusual in a way that doesn't say easy meal. Third, and maybe most importantly, why bother? There are almost always easier options. A predator with a healthy territory and a functional ecosystem has access to prey it knows, prey it's comfortable hunting, prey that fits its biological template. Going after something strange, unknown, and potentially dangerous when there's a perfectly available impala or rabbit in the vicinity makes no sense from a survival standpoint. The risk-reward math just doesn't work out. Here's something else that almost never comes up in these conversations. Your sleep is not as deep as you think. This is actually one of the more astonishing things about human biology. We experience sleep in cycles. You go down into deep, slow-wave sleep. Then you come back up into lighter stages, including REM sleep, where your brain is actually quite active. And during those lighter stages, researchers have found that your brain remains surprisingly responsive to the environment around you. External sounds still get processed. Unfamiliar noises are more likely to break through into awareness than familiar ones. Scientists call this the sentinel function of sleep. The idea is that even while resting, animals, including humans, maintain a partial watch on the environment. Your brain during light sleep stages is still filtering sensory input and flagging things that seem unusual or threatening. A twig snapping loudly nearby, the sound of a large animal moving through brush, a change in the air pressure and smell that comes with something large approaching. These things can pull you toward waking faster than you might expect. This is not an accident. The humans in our evolutionary history who slept too deeply, who were completely unresponsive to nighttime threats, were more likely to not wake up at all. The lighter sleepers, the ones who could go from asleep to on their feet in seconds, were the ones who survived and reproduced. Over hundreds of thousands of years, human sleep got tuned to stay light enough to respond to threats. We sleep lighter and in shorter cycles than most large mammals, partly because our evolutionary legacy assumed there would always be things in the dark worth waking up for. So, while you feel completely helpless when you're unconscious, you're actually running a fairly sophisticated early warning system. Not perfect, not foolproof, but present. And then there's the group factor. Humans are almost never actually alone when they camp. We travel in groups, sleep in groups, and those groups respond collectively. Predators across the animal kingdom understand group dynamics at a deep level because their prey animals also form groups. A wildebeest in the middle of a herd is much safer than a wildebeest at the edge. A fish in the center of a school is much harder to target than one that's been separated. Predators don't just attack prey, they hunt for separation. They look for the isolated individual, the one that's fallen behind, the one that's been cut off from the group. A camp full of sleeping humans is a group. And not just any group, a group that when one member wakes up and makes noise, will likely wake up the others. That collective response is deeply unappealing to a predator trying to make a clean, low-risk kill. The risk of a hunt going wrong, of turning into a chaotic group defense situation, is exactly the kind of thing predators are evolved to avoid. Now, let's be honest about something because this video would be irresponsible if it wasn't. None of this means you're untouchable. The attacks that do happen, and they do happen, follow a consistent pattern. They almost always involve circumstances that have broken the normal rules. A predator that's injured and can't hunt its normal prey. A predator that's starving because its habitat has been destroyed and its usual food sources are gone. A predator that's had so much contact with humans that it's lost its inherited wariness. This happens disturbingly fast when animals are fed by tourists or come to associate human presence with food rather than danger. Or a predator that's simply old and desperate, past its physical prime, unable to catch the prey it used to hunt. The lions of Tsavo in Kenya are the most famous example. In 1898, two male lions attacked and killed somewhere between 35 and 135 railway workers over about 9 months. The historical records disagree on the number, and the legend grew in the retelling. But what's often left out is that these were unusual lions. Both were maneless, which is atypical. One had severe dental damage that likely made its normal prey much harder to hunt. These weren't representative of lion behavior. They were exceptions created by exceptional circumstances. The Champawat tiger, responsible for an estimated 436 deaths in India and Nepal in the early 1900s, was later found by the hunter Jim Corbett to have been shot in the mouth at some earlier point, shattering 2 of its canine teeth. It could no longer hunt its natural prey effectively. It had been pushed by injury and then by habitat encroachment into hunting the only prey that was consistently available and physically manageable. The pattern repeats across almost every documented case of large predator attacks on humans in camp or at rest. Something broke. The normal calculation changed. The inherited caution got overridden by desperation, which means the rule holds almost universally in conditions where the ecosystem is intact, the predator is healthy, and the humans haven't done something to scramble the normal signals like leaving food out, approaching wildlife, or eliminating the campfire because it seemed unnecessary. There's one last layer to this that I saved for the end, because it's genuinely the most mind-bending part of the whole thing. We have been so effective at making the natural world afraid of us that it's now causing problems we didn't anticipate. That same 2019 UC Santa Cruz study didn't just document that pumas are afraid of humans. It documented that this fear cascades through the entire food web in ways that are difficult to fully control. When pumas avoid areas where humans are active, the deer in those areas face reduced predation pressure. Deer populations in those zones increase. That increased deer population overgrazes vegetation. Meanwhile, medium-sized predators, coyotes, bobcats, foxes, also reduce their presence near humans, which means the rodent populations they normally control start expanding. Everything shifts, and it shifts because of us, because of our presence, because the fear we've generated over millennia radiates outward through the ecosystem like a signal. We change the behavior of every predator layer on the continent without ever directly interacting with most of those animals. Just by being there. Just by being the thing that evolution told them to be afraid of. One species, one inherited fear, ripples across the entire living world. The most dangerous animal on the planet is the one that figured out fire before it figured out everything else. The one that's been shaping ecosystems not just through what it eats, but through what it makes other things afraid to eat. The one that sleeps light, travels in groups, and carries 10,000 generations of successful survival in its DNA. That's you. That's what you are. So, yeah. Next time you're lying in a tent in the middle of nowhere, listening to the sounds of the dark beyond the nylon wall, and you feel that little pulse of ancient anxiety, that's fine. That feeling kept your ancestors alive. But the thing outside the tent, it's not coming in. It knows better. Think about last night. You got into bed, you lay down, you closed your eyes, and then you woke up this morning. Somewhere in between those 2 moments, 8 hours vanished. Gone. Not just forgotten, but completely absent. There's no foggy version of the night you ever remember. There's no slow blur of memories getting hazier and hazier as the hours went on. One moment you were lying there thinking about something. Maybe something totally random, like why hot dogs come in packs of 10. And then nothing. Cut to black. Morning. And yet you have no memory of the actual moment it happened. You don't remember the last thought you had before your brain checked out. You don't remember your eyes getting heavy for the final time. You don't remember crossing that line between being awake and not. Why? This is one of those questions that sounds deceptively simple until you actually sit with it. You spend roughly a third of your entire life asleep, which means you've fallen asleep tens of thousands of times. You'd think by now you'd at least have some clue what it feels like, and yet every single night it happens without a trace. No goodbye, no warning, No last conscious thought you can actually hold on to. Just gone. The answer requires us to dig into some genuinely strange corners of neuroscience. And once you understand what your brain is actually doing during those final minutes of wakefulness, the mystery doesn't get smaller. It gets weirder. Let's start with what's physically happening in your brain as you fall asleep, because it is way more dramatic than most people realize. Throughout the day, every waking hour, your brain is burning energy. And as a byproduct of all that energy consumption, it produces a chemical called adenosine. Adenosine builds up slowly, continuously, from the moment you wake up, accumulating in your brain like a tab. At that, you're not allowed to close until bedtime. The longer you're awake, the more adenosine piles up. And adenosine doesn't just sit there quietly. It actively inhibits the brain's arousal systems, pulling down the systems that keep you alert, gradually making you feel heavier, foggier, more desperate to lie down. This is why you feel tired after a long day. This is also, by the way, why caffeine works. Coffee blocks adenosine receptors, so your brain can't read the "you're exhausted" signal. You're not actually getting more energy from coffee, you're just temporarily preventing your brain from knowing how tired it is. Which is a fun fact to think about when you're on your fourth cup of the day pretending you're fine. Alongside the adenosine buildup, your circadian rhythm, your internal 24-hour clock, controlled by a tiny region of the hypothalamus called the suprachiasmatic nucleus, starts dialing down its alerting signals as night approaches. The pineal gland releases melatonin. Body temperature drops slightly. The chemistry of your brain begins to shift, tipping the balance away from wakefulness and towards sleep. And then, when conditions are right, a kind of neurological switch gets flipped. Neurons in the ventrolateral preoptic nucleus, a small cluster of cells in the hypothalamus, start actively suppressing the systems that keep you awake. They inhibit the arousal centers. They quiet the signals pumping norepinephrine, serotonin, and histamine through your brain to maintain alertness. The brain essentially talks itself off the ledge of wakefulness. And at some point during this chemical negotiation, something critical happens to your thalamus. And this is where the memory piece starts to make sense. Your thalamus is, under normal waking conditions, the relay station of your brain. Everything you see, hear, feel, and sense passes through it on the way to your cortex. The thalamus is the reason you can hear a noise and consciously register it. It's why you can feel your sheets against your skin and know that's what you're feeling. It's constantly routing information from the outside world to the thinking, perceiving, experiencing parts of your brain. When you fall asleep, the thalamus essentially closes the gate. A structure called the reticular thalamic nucleus starts inhibiting the thalamus's relay cells, progressively cutting off the flow of sensory information to the cortex. The outside world, your phone buzzing somewhere across the room, a car going by, the hum of an air conditioner stops being forwarded upstairs. Your cortex, the part of your brain responsible for conscious experience and memory formation, starts getting starved of input. And without input, it can't really form new memories in any coherent way. This is already most of the answer. Right there. You can't remember falling asleep because the very process of falling asleep is one of your brain actively dismantling its own ability to record experience. The thalamus stops relaying. The cortex goes quiet. The encoding machinery for memory shuts down before you're even fully unconscious. So, the last few minutes of wakefulness are spent in a brain that is progressively less and less capable of actually logging what's happening. It's like trying to take a video on a phone whose battery is dying in real time. The footage from the last few seconds is going to be corrupted or missing entirely. Not because nothing was happening, but because the recording equipment gave out. But it gets stranger because your brain doesn't simply go quiet. There's a phase, probably the most underappreciated, scientifically fascinating, and genuinely surreal experience that every human goes through every single night called hypnagogia. And most people have absolutely no idea it's happening to them. Hypnagogia is the transitional state between wakefulness and sleep. Stage 1 sleep, technically. And during this window, which can last anywhere from a few seconds to several minutes, point 5, your brain is doing something deeply weird. The cortex isn't fully asleep. The thalamus is starting to close the gate, but hasn't shut it completely. And in that liminal zone, the brain starts producing spontaneous, involuntary sensory experiences. Hallucinations, essentially, though that word sounds more alarming than it needs to. What do hypnagogic experiences look like? Researchers who have woken people up during this phase report things like geometric shapes drifting across vision, sudden flashes of faces or places, the sound of a name being called, or a fragment of music, and the most classic one, the sudden sensation of falling immediately followed by a violent whole-body jerk that snaps you back to alertness. That jerk, called a hypnic jerk or sleep start, is experienced by an estimated 60 to 70% of people. You know the one. You're drifting off and suddenly you're falling off a non-existent ledge and your entire body convulses and your partner wants to know what is wrong with you. There's no definitive scientific consensus on exactly why hypnic jerks happen, though one popular theory suggests it's your brain misreading the muscle relaxation of sleep onset as a loss of balance and sending a quick emergency correction signal. Whether that's true or not, the body's response is immediate and extremely undignified. The visual association areas of the cortex remain active during this phase, generating vivid imagery without the anchoring input of actual vision. The temporal lobes, involved in auditory processing, show heightened activity, which may explain why people sometimes hear words or sounds that aren't there. But here's the critical thing. Most people wake up the next morning with zero memory of any of this. Not because it didn't happen, it definitely happened. But because the brain's memory encoding systems were already being shut down when it was occurring. The hippocampus, the brain's primary structure for converting experiences into long-term memories, is in a transitional state during hypnagogia. Some research suggests that N1 sleep, the hypnagogic stage, is actually associated with increased forgetting rather than memory formation. So, you lived through a genuine hallucination, possibly complete with geometric light shows and a dramatic false sensation of plummeting, and you remember none of it. Every night, without exception. Here's what makes this even harder to wrap your head around. The process isn't a clean, sharp line between awake and asleep. It's messy and gradual, and different parts of your brain don't all cross that threshold at the same time. Sleep researchers describe the onset of sleep as a local phenomenon. Different regions of the cortex can slip into something resembling a sleep state while other regions are still showing waking activity. This is why, if you've ever caught yourself nodding off somewhere embarrassing, a lecture hall, a particularly long meeting, that one cousin's wedding, you sometimes have a vague impression of something happening just before you jolted awake. Your motor cortex might have been more alert than your prefrontal cortex. Your auditory areas might have still been picking up sounds while your frontal regions had already vacated the premises. The result is that the exact moment of sleep onset, the moment that you'd need to remember in order to remember falling asleep, is genuinely not a single moment. It's a gradual region-by-region shutdown. By the time the regions responsible for memory formation and self-awareness are going offline, the regions responsible for recording that transition have already stopped working. The observer is the last thing to go, and it goes before it can write anything down. It's a bit like trying to film yourself going to sleep by holding the camera. Eventually, the hand holding the camera relaxes, the camera falls, and the last few frames are the ceiling spinning away as it hits the ground. Whatever happened in the final moments didn't get captured cleanly, and the camera definitely wasn't rolling when things finally went still. Now, add to all of this the fact that sleep itself doesn't particularly want you to hold on to the experience of falling asleep. Sleep is, among many other things, a memory consolidation process. During the night, your brain selectively strengthens certain memories formed during the day while quietly discarding others. It's doing maintenance, essentially, keeping what it thinks will be useful, pruning what it doesn't. Research has shown that this process is highly selective. Sleep doesn't just blindly reinforce everything, it makes judgments about what's worth keeping. The experience of transitioning into sleep itself, the dim, drowsy, fading final minutes of consciousness, is, from the brain's perspective, probably not high on the worth-keeping list. It contains no actionable information, no emotional significance, no survival-relevant content. It's just the feeling of lying in the dark, getting progressively hazier. Your brain is a ruthlessly practical editor, and it has collectively decided across the entire human species and every night of recorded history that the experience of falling asleep is content that ends up on the cutting room floor. Meanwhile, the hippocampus, which, remember, is key to forming new episodic memories, actually shows some interesting activity during the transition into sleep. including what researchers believe might be a kind of rapid memory processing. But these aren't memories being formed. These might be recent memories being tagged, sorted, evaluated. The hippocampus during sleep onset is the overnight editor going through the day's footage and deciding what makes it into the final cut. And the act of editing is not itself in the movie. There's also a strange philosophical dimension to all of this that's worth sitting with for a moment. The fact that you can't remember falling asleep means there is a regular nightly gap in your subjective experience that you are completely unaware of. You experience yourself as a continuous being living through one connected thread of consciousness from when you wake up to when you go to bed. But that thread is broken every single night, and you don't notice because the part of you that would notice is the same part of you that goes offline. You are not present for approximately 8 hours every 24, and you have no felt sense of that absence because feeling the absence of consciousness would itself require consciousness. The ancient Greeks intuited something like this. Aristotle described sleep as a state between living and not living. The Greeks associated sleep with Hypnos, the god of sleep, and his twin brother Thanatos, the god of death. Not because they thought sleep was dangerous, but because there was something philosophically troubling about the nightly suspension of the self. You go to sleep, and in some meaningful sense you stop. And then something that claims to be you picks up where things left off in the morning with no direct memory of the gap. We're generally fine with this because we wake up feeling like the same person, with our memories intact, our personality unchanged. The continuity feels preserved even though there's a discontinuity baked into every night. But the feeling of continuity and the fact of continuity are not quite the same thing. And the question of what exactly persists through sleep is one of those questions that sounds like philosophy homework until you've had too much caffeine, possibly borrowed from your future tired self. And you're lying in bed at 2 a.m. thinking about it. So why can't you remember falling asleep? Because your brain starts shutting down its own recording equipment before it goes fully offline. The thalamus closes the gate on incoming sensory information, cutting off the data stream the cortex uses to build conscious experience and memory. The hippocampus shifts away from encoding new long-term memories and begins its nightly maintenance work. The prefrontal cortex, the region most responsible for self-awareness, for the sense of being a coherent self monitoring its own experience, is among the first regions to drop offline. And by the time all of that is happening, there is no longer a version of you awake enough to notice any of it. In between your last clear memory and the alarm going off, there was a whole transitional event. The closing of the thalamic gate, the hypnagogic hallucinations with their geometry and phantom sounds, probably at least one dramatic hypnic jerk, the slow cortical shutdown region by region, a full neurological performance happening without an audience, because the audience is simultaneously the performer and the one falling asleep. Every night you essentially vanish, and you're okay with it, because you always come back. The brain decided a long time ago that this was a reasonable trade. 8 hours of absence in exchange for a repaired, consolidated, functional version of yourself the next morning. Memory of the transition was not included in the deal, and honestly, given how strange that transition actually is, given the geometric hallucinations and the phantom ledge you keep falling off, and the progressive regional shutdown of your own consciousness, maybe it's for the best that you don't remember it. You'd never get any sleep. Word count check. Approximately 2,980 words, below the 3,300 word minimum. Expanding now. Let's actually take a closer look at the hypnic jerk, because it deserves more attention than it gets, and because it's one of the best examples of your brain being completely unhinged in a way you've normalized. You're lying there, calm, getting drowsy. Your muscles are beginning to relax, a process your brain is actively initiating as part of sleep preparation. Heart rate is slowing, breathing is getting shallower, everything is going according to plan, and then your brain panics. In one of the most spectacular examples of the brain catastrophically misreading a situation, some part of the transitioning nervous system interprets the sudden drop in muscle tension as evidence that the body is falling. Not lying down deliberately, actually falling. And so it fires a rapid, uncontrolled emergency signal through the motor system, telling every major muscle group to please catch yourself immediately. Hence the jerk. Hence the gasping. Hence the extremely undignified flailing that has startled countless sleeping partners throughout all of human history. One popular theory, as mentioned, is that this is a primitive reflex, a vestige from ancestors who slept in trees where sudden muscular relaxation really would have been a problem, and a reflexive grip and grab response would have been genuinely useful. Whether that's accurate or not, the reflex clearly never got the memo that humans moved inside and started sleeping in beds on flat ground. It persists, it fires, and it makes you look absolutely ridiculous in front of anyone who happens to be watching. And here's the twist. Even when the hypnic jerk wakes you up, even when you snap back to full awareness because your body just threw itself, you usually don't remember what was happening right before. The hypnagogic state that preceded it, whatever images or sounds your brain was hallucinating in that strange twilight zone, has already been lost. The jerk wakes you up, you're briefly confused, maybe slightly embarrassed, and within a minute or two you're drifting off again. Straight back into the same process you have absolutely no memory of going through moments before. The brain is doing the same thing over and over and storing none of it. There's another angle to this that's worth exploring. What happens when people get woken up during different stages of sleep onset and are asked to report what they were experiencing? Because sleep researchers have actually done this in labs for decades, and the results are illuminating. When you wake someone up during the early hypnagogic phase, the very beginning of stage 1 sleep, they often report fragmented, disconnected imagery. Single images like a face, a color, a shape, with no narrative. Like a PowerPoint presentation built by someone who has never seen a PowerPoint presentation. No story, no continuity, just isolated visual fragments. A little deeper in, and the reports become stranger. Scenes start to acquire more detail. There might be a half-formed sense of place. Sounds appear. Sometimes there's a fleeting awareness of a logical structure, like the beginning of a dream plot. But it dissolves almost immediately when the person is woken up. Ask them to describe it 30 seconds later, and it's already slipping away. Ask them a minute later, and it's gone completely. This is the opposite of how we usually think about dreams. With proper REM sleep dreams, the ones deeper in the night, there's at least a chance you'll remember them, especially if you wake up during or immediately after. The hypnagogic experiences at sleep onset are so fragile, so loosely encoded, that they essentially exist only in the moment and then evaporate. They are in some sense the least sticky memories the human brain ever produces, which is saying something given how bad we are at remembering things in general. What this means is that you have a nightly experience that is psychedelic, bizarre, and entirely your own, and you will almost certainly carry zero evidence of it into the morning. Night after night, your brain produces a private light show and then immediately destroys the tape. One more layer here, and then we can tie this all together. There's a concept in sleep science sometimes called sleep state misperception or paradoxical insomnia. It describes people who are convinced they barely slept, who wake up certain they were awake for most of the night despite objective measurements from sleep labs showing they were asleep for perfectly normal amounts of time. And while this sounds like the brain just being unreliable, which it very much is, it points at something important. Our subjective sense of being awake or asleep is genuinely not trustworthy. Some people swear they heard every minute of the night ticking by. They insist they were conscious, lying there unable to sleep. But the EEG, the brainwave measurement that objectively shows sleep stages, says otherwise. They were in stage 1, stage 2, maybe even deeper, while their subjective experience was one of continued wakefulness. The brain can be in a measurable sleep state while still telling the conscious mind, or what's left of it, we're definitely awake. This is fine. We're not asleep at all. Which means the question, when did you fall asleep, may not even have a clean answer, not just philosophically but neurologically, because your brain's state and your brain's story about its state can come apart. The machinery can go into sleep mode while the little narrator in your head is still running its commentary, insisting it's awake, until presumably even the narrator quietly steps away from the microphone. And the commentary just stops and you don't notice because you're asleep. So here's the complete picture. You can't remember falling asleep because it involves a cascading, overlapping series of processes that collectively destroy the conditions necessary for memory formation before you're even unconscious. Adenosine and melatonin and a cascade of neurochemistry tip the brain away from wakefulness. The hypothalamus flips the arousal system toward off. The thalamus closes the gate on sensory input, cutting off the data stream to the cortex. The hippocampus shifts away from encoding new experiences. The prefrontal cortex? The last most executive part of you, the part that maintains self-awareness and monitors what's happening, powers down. And somewhere in all of that, the part of you that could record the experience stops existing before the experience fully ends. The hypnagogic hallucinations come and go unremembered. The hypnic jerk fires and fades. The brainwaves slow from alert beta through relaxed alpha into drowsy theta, and the transition happens without a witness. By the time you're fully asleep, every system that would have been needed to document the process of getting there has already been shut down. It's one of those things that seems like a flaw, a gap in the system, an inexplicable absence, but it's actually the system working exactly as designed. Your brain isn't failing to capture the moment you fall asleep. It's prioritizing sleep over documentation. And every morning you pick up where you left off, feeling like a continuous self who simply went to sleep and woke up with no awareness of the nightly suspension of consciousness, the brief hallucinations, the memory wipe, or the regional shutdown and restart of your own experience. You fall asleep thousands of times in a life. You'll never remember a single one, and somehow that's completely fine. It's roughly 170,000 years ago. You're a human, barely recognizable as one, but still. You wake up, stretch, look around at the African savanna, and at absolutely no point do you think you know what would really complete this morning. Pants. And yet, here we are, billions of people every single morning putting on pants or skirts or whatever you call that thing that's technically pajamas, but you've been wearing for 3 days straight and you're calling it loungewear now because that sounds intentional. Clothes are so baked into human existence that we literally arrest people for not wearing them. Think about that for a second. The state will intervene if you're too naked. We built an entire legal system around the concept of please put something on. We have laws about nudity as a species. That is where we are. But why? When did this start? And more importantly, why did we do it when basically every other animal on the planet just didn't? Dogs don't wear clothes. Wolves don't wear clothes. The elephant, which is objectively smarter than most people you went to high school with, has never once thought, I need a jacket for this. The short answer is we have no idea exactly when it happened. The long answer is way more interesting and slightly weird, and it involves lice, which, spoiler, is not as gross as it sounds. Actually, it is. It's exactly as gross as it sounds, but stick with it, because the lice thing is genuinely one of the most bizarre and fascinating pieces of evolutionary detective work in all of science. Let's go back to the beginning. The naked ape problem. Here's something nobody talks about enough. Humans are basically the only large mammals on Earth that are nearly hairless. Genuinely stop and think about that zoologically for a second. Gorillas, covered. Chimpanzees, covered. Bears, lions, wolves, horses, elephants, hippos, all of them across wildly different environments and climates are walking around in full coats. And then there's us, standing in the middle of all this biodiversity, just smooth, a bit patchy. Weirdly pink in some places, sporting an evolutionary look that says, I used to have fur, but I made some choices. Scientists have a few theories for why we lost our fur in the first place. The most popular one is the thermoregulation argument. Basically, as our ancestors moved from forests to open grasslands and started running long distances to hunt, being covered in thick fur became a massive liability. You'd overheat. You'd slow down. Your core temperature would spike, and you'd collapse before catching the thing you were chasing. And then you'd die hungry, which from an evolutionary perspective is the worst possible outcome. So, over hundreds of thousands of years, we gradually shed our fur and developed something better. An absolutely insane number of sweat glands. Humans have approximately 2 to 4 million sweat glands on their bodies. That is more than almost any other animal on the planet. We are, without exaggeration, elite sweating machines. Professional grade, world-class moisture emitters. If there were Olympics for sweating, we would dominate every category. This is great in the summer. It is considerably less great when it's 40 below zero and you're trying to survive in Central Asia with nothing but your wits and a rock. And that's where clothes come in. Eventually, warmth was probably not the first reason. Probably. Here's the conventional story. Humans moved out of Africa, hit colder climates, got cold, wrapped themselves in animal skins, and that's that. Simple, clean, logical. A 5-year-old could figure it out. Except the timeline doesn't quite work, and once you notice that, the whole tidy narrative starts to unravel. Genetic evidence, which we'll get to in about 30 seconds, suggests that humans started wearing clothes somewhere around 100,000 to 170,000 years ago. The problem is that modern humans didn't really start migrating out of Africa in significant numbers until around 70,000 years ago. So, if clothes were purely a response to cold weather, why are they appearing tens of thousands of years before humans actually went anywhere cold? Something else must have been going on earlier, something social, something that has more to do with who we are as a species than with the temperature outside. But before we get into that, we need to talk about the most unlikely piece of evidence in the entire clothing origin story. And yes, it's the lice. We're doing the lice now. The louse that changed everything. Researchers at the University of Florida were doing what geneticists do, which apparently involves staring at very small things for extremely long periods of time and occasionally having a breakthrough that changes everything. And they decided to map the evolutionary history of human lice. Now, here's the crucial piece of biology you need to understand. Humans have two main types of lice, head lice and body lice. Head lice live in your hair. Body lice live specifically in clothing, in the seams, in the folds, in the fabric. They are two genetically distinct populations, and body lice evolved from head lice at some specific moment in history. Here's why that matters enormously. Body lice can only survive if there are clothes to live in. They cannot survive on bare human skin. They need fabric. They need the warmth and shelter that clothing provides. So, the moment body lice genetically diverged from head lice, the moment that evolutionary split happened is essentially the moment humans started wearing clothes consistently enough to create a new ecological niche for a parasite. When researchers ran the numbers, they found that body lice diverged from head lice somewhere between 83,000 and 170,000 years ago. Let that sit for a moment. A parasitic insect, one of the most universally hated creatures in human history, the thing that causes mass panic in elementary schools and ruins camping trips, accidentally preserved the earliest evidence of human fashion. The lice know when we got dressed before we do. They were there, they adapted, they moved in. That is either beautiful or deeply, deeply horrifying. Possibly both simultaneously. Probably both. So, what were clothes actually for first? Okay. So, we've established that clothing predates the migration out of Africa by a significant margin, which means warmth cannot be the original driver. So, what was? Theory number one, basic physical protection. Not from cold, but from sun, insects, sharp vegetation, and general abrasion. If you're spending your days walking through tall grass and thorny scrubland, tracking animals across rocky terrain, a basic wrap or loincloth made from animal hide creates a meaningful barrier between your skin and things that want to scratch, bite, or burn it. It's not glamorous, it's not philosophically interesting, but it probably kept early humans significantly more comfortable and reduced infections from small cuts and wounds. Sometimes the boring answer is the right one. Theory number two is where it gets genuinely interesting: social signaling. Humans are, at our core, profoundly social animals. We are obsessed with hierarchy in a way that goes bone deep. We are constantly, compulsively communicating who we are, what group we belong to, what status we hold, whether you should be scared of us, or attracted to us, or deferential to us. We do this with our posture, our facial expressions, our voices, our hairstyles, our tattoos, and quite possibly from very early on with what we drape over our bodies. There's evidence that our ancestors were using pigments like ochre for body decoration as far back as 200,000 years ago. That's before the lice evidence for clothing. So the impulse to decorate the body to signal something visually about yourself to the group that may actually be older than clothing itself. We were painting ourselves before we were dressing ourselves. The jump from decorating your skin to wearing a particular kind of hide in a particular way isn't a large cognitive leap. And once the hide is on, you start thinking about which hide and how it's worn and what that communicates. Is this the hide of something powerful? Did I kill it myself? Does wearing it say something about me? Welcome to the very first fashion industry. Population. A small band of Homo sapiens on the African savanna arguing about who gets to wear the leopard skin. Needles, awls, and the invention of tailoring. For most of early human history, clothing probably looked rough. A skin draped over the shoulders, held in place with a cord made of twisted sinew, maybe crudely cut along the edges with a stone flake. Functional, ungainly. The prehistoric equivalent of wearing a bin bag. Gets the job done, but nobody's winning any awards. But then, around 50,000 years ago, something changes in the archaeological record. Researchers start finding bone needles. Not just pointed tools for punching holes, actual needles with tiny eyes bored through them, clearly designed for threading sinew or fiber and stitching material together with precision. Fitted clothing, sewn seams, garments shaped to the body rather than just thrown over it. The oldest confirmed needle with a proper eye was found in Denisova Cave in Siberia and dates back approximately 50,000 years. It was made from the hollow bone of a bird, shaped and polished to a fineness that is genuinely extraordinary. This object represents a cognitive leap that is difficult to overstate. Someone looked at a sliver of bone, envisioned a tool that didn't yet exist, figured out how to bore a clean hole through the narrow end without splitting it, and used the finished product to join two pieces of material with a controlled, repeatable stitch. That is not survival instinct. That is engineering. That is design thinking. That is someone solving a problem through imagination and craft rather than brute force. And that needle matters more than almost any other object from that period because you can live without pottery, you can live without cave paintings. In Siberia, 50,000 years ago, in the depths of a glacial winter without properly fitted clothing that seals heat against the body, you absolutely cannot. The Neanderthals were doing it too. Here's something that often gets dropped from the clothing origin story, mostly because it complicates the neat modern humans invented everything narrative. Neanderthals were also making and wearing clothes, and they were doing it well before they ever encountered us. We've found substantial evidence of Neanderthals systematically processing animal hides, scraping bones in patterns consistent with hide preparation, using specific stone tools that were clearly designed for working leather, and managing carcasses in ways that suggest they were after the skin as much as the meat. There's also genetic and anatomical evidence suggesting Neanderthals had physiological adaptations to cold climates, stockier bodies, shorter limbs, different fat distribution, which tells us they were dealing with serious cold for a very long time. Clothes would have been essential, not optional. And then there are the Denisovans, the mysterious third human lineage we only discovered in 2010 from a single finger bone found in that same Siberian cave. In the same archaeological layers as the needle, researchers found pierced and polished ornaments that suggest symbolic thinking, decoration, and possibly garment embellishment. A people we barely know existed were already thinking about what they were wearing and how it looked. So the impulse to clothe the body wasn't exclusive to our lineage. Multiple human species in different environments arrived at similar solutions through overlapping reasoning, which raises a genuinely unsettling question. Is clothing a human thing, or is it a smart bipedal primate living in a harsh environment thing? Is it inevitable? Would any sufficiently intelligent creature, cold enough and social enough, eventually figure out that wrapping yourself in something is just obviously correct? We don't know. But the convergence across species is very hard to dismiss. Let's take a step back and talk about the truly strange thing here. The thing that separates human clothing from every other animal's relationship with shelter or protection. If clothes were purely practical, every culture across history would converge on the most thermally efficient solution for their climate and just stay there forever. Thick hides in the Arctic, light plant fiber in the tropics, same shapes, same function, total standardization. Done. That is categorically not what happened. What happened is that humans immediately and universally made clothing mean something. In every culture we have records of, going back to the earliest archaeological evidence, clothing carries symbolic weight that goes far beyond its physical function. Priests wore different things than warriors. Rulers wore things nobody else was allowed to wear. The dead were buried in specific garments suited to their status and the journey ahead of them. Ceremonies required specific dress that would be absurd in any other context. Some of the oldest textile fragments ever found weren't just pieces of fabric. They were dyed in multiple colors. Someone, tens of thousands of years ago, looked at a perfectly functional piece of woven material and thought, this needs to be a different color. Not because it would keep them warmer, but because it would mean something different, because it would say something. This is the fundamental weirdness of human clothing. We use it as language. We use it to construct and broadcast identity. We use it to say, I belong to this group, I hold this rank, I am mourning, I am celebrating, I am dangerous, I am available, I am sacred, I am ordinary. No other animal does this. Peacocks display, sure. Cuttlefish change color, but they're not choosing what to communicate based on social context, cultural history, and personal narrative. That's entirely ours. And it started, as best we can tell, in Africa between 1 and 200,000 years ago, when some ancestor of ours picked up a piece of ochre, painted themselves with it, and felt something click into place about who they were in relation to everyone else. Even if warmth wasn't the original reason, it became a survival-critical one fast. Between roughly 120,000 and 70,000 years ago, Earth went through a series of brutal glacial cycles. Global temperatures plunged, ice sheets expanded dramatically, large portions of Africa became hyper-arid, lakes dried up, food sources collapsed. The human population may have crashed to somewhere between 10 and 30,000 individuals at its lowest point. We nearly went extinct. We came astonishingly close to just not existing anymore as a species before we'd even gotten properly started. For the survivors, and especially for the groups that eventually pushed north into Europe and east into Central Asia over the following millennia, clothing was no longer a social signal or a practical comfort. It was the thin line between life and death, quite literally. The groups that had already developed sophisticated clothing technology, fitted, layered, stitched, sealed at the extremities, had a survival advantage so significant, it's hard to overstate. A properly constructed garment traps warm air against the body. It protects the wrists and neck, the places where blood runs close to the surface, and heat escapes fastest. It allows a human body to survive temperatures that would kill an unclothed person in hours. Those with the needle, the thread, the knowledge of how to prepare hide and layer materials, they made it through. They had children, those children learned the same skills, and those skills carried forward across generations are part of the reason modern humans made it to every continent on Earth. We didn't just evolve bodies suited for the world, we built a second skin and carried it everywhere we went. There's a transition in the clothing story that often gets glossed over because it doesn't have a single dramatic moment attached to it. The shift from animal hides to woven plant fibers. Animal hides are warm, durable, and water-resistant. They're also heavy, stiff, difficult to clean, and you need to kill something to get them, which is a logistical constraint. At some point, humans started working with plant fibers, spinning them into thread, twisting them into cord, eventually weaving them into fabric. The oldest known twisted plant fiber was found in a cave in the Republic of Georgia, the country, not the state, and dates to roughly 30,000 years ago. Crucially, those fibers were dyed in multiple colors. Already decorative, already intentional, already communicating something beyond simple function. By the time of the Neolithic agricultural revolution, roughly 10,000 BCE onwards, textile production had become a core technology of human civilization. Flax cultivation for linen, wool from domesticated sheep, eventually cotton, silk, and the extraordinary variety of fibers that different cultures developed independently across the world. And with textiles came something genuinely revolutionary. The wardrobe, clothing that could be specialized for different purposes. A heavy cloak for winter, a light wrap for summer, specific garments for ritual, for work, for status, for mourning. Clothing as a system of expression rather than a single object of survival. The textile industry, long before the Industrial Revolution made it mechanical, was one of the most significant economic and cultural forces in the ancient world. Entire trade routes were built on it. Empires were financed by it. Wars were fought over access to the raw materials for it. Silk alone reshaped the political geography of half the world. All of this from a cold, naked primate with clever hands and a piece of bone. So, why did ancient humans start wearing clothes? The honest answer is for all the reasons, in overlapping waves, driven by biology and culture and climate and social complexity all at once. It probably started with practical protection, something between the skin and the thorns and the sun and the biting things. It evolved almost immediately into social signaling, a way of saying something about who you are in a world full of other people making constant judgments about you. It became a survival technology when the climate turned hostile and the migrations began. And it became an art form, an industry, a language, and an identity as human culture grew more complex. The remarkable thing isn't that we started wearing clothes. Given who we are, social, symbolic, status-obsessed, freezing half the time, it was probably inevitable. You are doing that right now. Whatever you're wearing, you made choices, conscious and unconscious ones about what to put on your body today. And those choices reflect something about who you are, how you feel, what group you belong to, what image of yourself you're presenting to the world. You are doing exactly what that person on the African savannah was doing, wrapped in ochre-stained hide, figuring out how to signal something about themselves to the people standing around the same fire. 150,000 years of human history, and what connects you to them directly, without interruption, is the simple fact that you got dressed this morning. That's not a small thing. That's the whole thing. We get cold, we get creative, we get dressed, and then we spend the rest of our lives complaining that we have nothing to wear. Some things genuinely never change. And what about you? Would you go back in time and live completely naked? Let me know in the comments. Until then, see you soon. You're standing around a fire. It's 50,000 BC. The sun just went down. There's no Netflix, there's no phone, there's no existential dread about your inbox. There's just you, the flames, and the thick choking smoke curling directly into your face. And somewhere at some point, one of your ancestors looked at that smoke and thought, wait, what if I did that on purpose? This is the story of how humans discovered smoking. Not cigarettes, not cigars, not the guy outside the office who you always end up talking to for too long. We're talking about the very first time a human being intentionally inhaled something burning, and why that might be one of the oldest habits our species has ever had. Because here's the thing nobody tells you. Smoking doesn't start with tobacco. It doesn't start with colonial trade routes or Native American ceremonies or even agriculture. The desire to inhale smoke might be hardwired into us on a level so deep it predates civilization entirely. And the evidence for this is genuinely insane. Let's start with fire. Because before you can smoke anything, you need fire. And fire has been part of the human story for a very, very long time. The oldest confirmed evidence of controlled fire used by our ancestors dates back roughly 1 million years from a site called Wonderwork Cave in South Africa. Archaeologists found burnt plant ash and charred bone. Not the result of a wildfire, but of a sustained contained fire used deliberately inside a cave. Now, 1 million years ago, we weren't even Homo sapiens yet. That was Homo erectus, our earlier cousin with a smaller brain, a heavier brow, and absolutely zero interest in being told what to do with it. They sat around fires just like we do. They cooked, they stayed warm, they huddled together in the dark, and they breathed smoke. Every single day for hundreds of thousands of years, every human and pre-human ancestor who sat near a fire inhaled smoke. It was unavoidable. It was constant. It was basically the original air quality situation, and nobody had an app to check it. But here's where it gets interesting. Some of that smoke wasn't just wood smoke. When you burn organic matter, you don't just get carbon dioxide and water vapor. You get a cocktail of compounds depending on what you're burning. Some plants, when combusted, release psychoactive chemicals, alkaloids, terpenes, compounds that interact with the human nervous system in ways that are, let's say, noticeable. In other words, some of our ancestors were absolutely accidentally getting high around the campfire, and they had no idea why they felt amazing. This isn't a fringe theory. Researchers have proposed for decades that early humans living in forested environments would have regularly been exposed to the smoke of psychoactive plants like cannabis, Nicotiana species, and various entheogens that grow naturally across Africa, Europe, and Asia. The human brain, it turns out, has receptors that respond to cannabinoids. These receptors didn't evolve because of cannabis. They're part of our endocannabinoid system, which regulates everything from mood to memory to appetite. But the fact that they exist means that when a human first inhaled smoke from a burning cannabis plant, their brain wasn't confused. Their brain was like, oh, hello, I've been waiting for you. And that moment, that first accidental hit of psychoactive smoke around a prehistoric campfire, might be the true origin of smoking. Not a decision, not a plan, just a very pleasant accident repeated enough times that someone eventually thought to recreate it on purpose. Think about that for a second. The entire multi-trillion-dollar global tobacco industry, the centuries of ritual, the shamanic traditions, the medical practices, the social customs, all of it may have started because a tired hunter sat downwind of the wrong bush and had a really unexpectedly great evening. History is sometimes beautiful in the most absurd ways. Now, here's where we have to be careful about timelines, because ancient humans smoked things, and ancient humans intentionally cultivated things to smoke are very different claims. Let's talk about what the archaeology actually tells us. The oldest direct evidence of intentional cannabis use, meaning burned cannabis seeds found in a context suggesting deliberate inhalation, comes from a burial site in the Pamir Mountains of Central Asia, dating to around 500 BC. Excavators found wooden braziers containing stones that had been superheated alongside residue from cannabis plants with unusually high THC content. This wasn't wild cannabis used for rope or seeds. This was the good stuff. And it was placed directly in a ritual burial context, 500 BC. That's roughly 2,500 years ago. But here's the question that should be sitting in the back of your mind. Does the absence of older physical evidence mean it didn't happen earlier? Or does it just mean we haven't found it yet? Because organic material, seeds, leaves, plant fiber almost never survives thousands of years in the ground. We find stone tools from 3 million years ago because stone is basically indestructible. But a wooden pipe filled with dried herbs that's gone in a few centuries under normal burial conditions. A leather pouch of cannabis dissolved back into the earth long before any archaeologist ever showed up with a trowel. So the absence of evidence in this case is absolutely not the evidence of absence. There is also the Herodotus problem. Herodotus, the ancient Greek historian writing in the 5th century BC, described in remarkable detail the Scythians, a nomadic people from the Eurasian steppe, performing what he called a vapor bath. They would set up small enclosed tents, heat stones until they glowed, and throw hemp seeds onto those stones, then sit inside the tent inhaling the smoke, and, as Herodotus wrote, howling with pleasure. For centuries, historians assumed he was exaggerating or misunderstanding what he saw. Then archaeologists started excavating Scythian burial mounds and finding, you guessed it, bronze braziers, heated stones, and hemp residue. Exactly what Herodotus described. The man was just reporting what he saw. He wasn't embellishing. He was, if anything, underselling it. Let's talk about tobacco because it's the one most people actually associate with smoking. Tobacco is a plant in the genus Nicotiana, and it's native to the Americas. That matters enormously because it means tobacco was completely unknown to Old World civilizations, Europe, Africa, Asia, until contact with the Americas in the late 15th century. When European explorers arrived in the Caribbean in 1492, they immediately noticed indigenous people doing something strange. Columbus himself wrote in his journal about seeing men and women walking around with small glowing sticks, inhaling the smoke from burning dried leaves, and letting it back out through their noses and mouths. His crew was baffled. His crew also, within weeks, tried it themselves, because of course they did. But tobacco use in the Americas is far, far older than 1492. Archaeological evidence of tobacco, specifically chemical residues in ancient pipes, has been found dating back to at least 3,500 years ago in the southeastern United States. Some researchers believe it could go back considerably further, possibly 10,000 years or more, tied to the development of cultivation in the Amazon basin. And here's the thing about tobacco in ancient America. It was not recreational. Not primarily, it was sacred. Tobacco was used in healing rituals, in communication with the spirit world, in binding agreements between tribes. Blowing smoke on someone was an act of blessing, of connection, of respect. A shaman who smoked wasn't having a casual cigarette break. He was opening a channel between the living and the divine. The smoke itself was considered a living carrier, a messenger that traveled between worlds, carrying prayers upward and bringing visions downward. That framing matters. It explains why tobacco use was so disciplined, so ritualized, so controlled in many indigenous cultures for thousands of years. When something is sacred, you treat it with reverence. You don't chain smoke it while watching TV. The idea of tobacco as a casual everyday habit, something you do on a lunch break or while waiting for the bus, is an almost entirely European invention, and a fairly recent one at that. Now, let's go back even further because there's a piece of this story that most people have never heard, and it might be the oldest evidence of intentional smoking in the entire archaeological record. In 2019, researchers made a remarkable discovery at a site in the Great Salt Lake Desert in Utah. They found a hearth, a cooking and heating fire, roughly 12,000 years old, containing the seeds of Nicotiana attenuata, a wild tobacco species native to North America. These weren't seeds that had accidentally blown into the fire. They were concentrated, present in a way that suggested deliberate placement. The site predates any known pottery or pipe artifacts in the region by thousands of years. This pushed back the possible timeline of tobacco use in the Americas by a significant margin, and it raised a genuinely fascinating question. If people were throwing tobacco into fires 12,000 years ago, whether to inhale the smoke or for ritual purposes or both, what were people in other parts of the world doing with their local psychoactive plants at the same time? Because 12,000 years ago, humans were everywhere. They were in Africa, in Asia, in Europe, in Australia. And the human desire to alter consciousness, to seek out altered mental states, that is not an American phenomenon. That is a human phenomenon. Let me throw something at you that might sound wild, but is taken seriously by respected anthropologists: the intoxication hypothesis. The basic argument goes like this. Across virtually every human culture ever documented, people have sought out ways to alter their consciousness. They've drunk fermented beverages, eaten psychedelic mushrooms, inhaled smoke, chewed plant leaves, and swallowed seeds. This behavior is so universal, so persistent, and so independent across cultures that some researchers believe it isn't accidental. Ronald Siegel, a psychopharmacologist at UCLA, proposed in the 1980s that the pursuit of intoxication is a fourth drive alongside hunger, thirst, and sex that is biologically embedded in animal behavior, not just human behavior. Elephants deliberately seek out fermented marula fruit. Reindeer in Siberia have been observed eating Amanita muscaria mushrooms and then drinking the urine of other reindeer who ate the mushrooms because the psychoactive compounds pass through intact. Reindeer doing drug recycling in Siberia. Honestly, respect. The point is, if the drive to alter consciousness is this deep and this old, it's entirely reasonable to propose that early humans, long before they domesticated any plant, long before they had pottery or pipes or any of the tools we normally associate with smoking, were deliberately exposing themselves to smoke from psychoactive plants because they had learned through experience that it changed something in their mind. Maybe they burned those plants intentionally during rituals. Maybe they selected campsites near specific plants for exactly this reason. Maybe they learned which smoke made you feel good and which made you feel like you were dying, which with some plants is a distinction that kills you once before you figure it out. This is trial and error, prehistoric style, very high stakes, occasionally literally fatal. But the ones who survived, they remembered. They told others, they passed it down through generations of knowledge that never got written, but got lived. That's how most human knowledge worked for most of human history. Not libraries, not schools, lived experience passed mouth to ear around a fire in the dark. Let's also talk about something that rarely comes up in this conversation: smoking as medicine. Long before smoking was recreational, long before it was spiritual, it may have been medical. The Ebers Papyrus, one of the oldest known medical documents in the world, dates to ancient Egypt around 1550 BC. It describes treatments involving the inhalation of smoke from heated herbs, specifically for conditions affecting the throat and lungs. This is wildly counterintuitive from a modern perspective. You're telling me the ancient Egyptians treated lung problems by inhaling smoke? Yes. Yes, they were. And while that seems insane, it's worth noting that the specific herbs they used, including henbane and various aromatics, do have genuine pharmacological properties when inhaled. The ancient Greeks used fumigation, Therapeutic smoke? Regularly. Hippocrates, the guy you take an oath named after if you become a doctor, wrote about the inhalation of herbal vapors to treat diseases of the lungs and other conditions. The thinking wasn't crazy by the standards of the time. Smoke reaches the lungs directly, so if the plant has medicinal properties, delivering it via smoke makes a certain logical sense. The lungs as a delivery mechanism. Inhaled medicine. We still do this today with asthma inhalers and anesthetic gases and nebulizers. The delivery method survived. The burning part, thankfully, mostly didn't. Ancient Indian Ayurvedic medicine, dating back over 3,000 years, describes a practice called dhumapana, literally smoke drinking, involving the inhalation of medicinal herbs through pipes. The texts describe specific plants, specific conditions. This wasn't casual or improvised. It was a sophisticated medical system with detailed protocols and centuries of refinement behind it. Across ancient China, ancient Mesopotamia, ancient Greece, ancient India, in virtually every early civilization on record, there is evidence of people inhaling smoke deliberately for therapeutic purposes as a recognized medical practice. Not because they were addicted, not because they thought it was cool, because it worked, or at least it worked sometimes. Or at least it worked enough times that they kept doing it. And in a world without antibiotics, without surgery, without any of the tools modern medicine takes for granted, works sometimes was a pretty meaningful bar to clear. There's another angle to this story that doesn't get enough attention, and it has to do with social bonding. Humans are deeply social animals. We evolved in groups, and group cohesion, the ability of a group to stay together, trust each other, act in coordination, was literally a matter of life and death for most of our evolutionary history. Isolated individuals died. Groups survived. Anything that enhanced social bonding had genuine survival value. And shared rituals, including shared consumption of psychoactive substances, are extraordinarily powerful tools for social cohesion. When a group of people undergo a shared altered experience together, it creates a sense of connection, of trust, of mutual understanding that is very hard to replicate any other way. Modern neuroscience has confirmed this. Shared rituals synchronize neural activity, increase trust, and deepen group identity in measurable, documented ways. So, when a group of ancients sat together in a closed space breathing in smoke from burning cannabis or other herbs and collectively entered an altered state, that wasn't just recreational. That was social technology. That was how you built the kind of deep trust and group cohesion that let you go into dangerous situations together and come back alive. The ritual smoke circle wasn't just a party. It was infrastructure. Here's where we arrive at the uncomfortable part of the story. The transition from sacred smoke to casual habit is historically an absolute disaster. When tobacco arrived in Europe in the 16th century, it spread with a speed that should remind you of something. Within decades, smoking had gone from an exotic curiosity to a continental obsession. By the 1600s, tobacco was being traded globally. By the 1700s, snuff, powdered tobacco inhaled through the nose, was fashionable across European aristocracy. By the 1800s, cigars were everywhere. By the early 1900s, the industrially manufactured cigarette had been invented, making tobacco consumption cheaper, more convenient, and more addictive than anything that had come before. What had taken indigenous Americans thousands of years to incorporate into a measured, ritualistic, deeply cultural practice was, in the hands of European industrialists, turned into a mass-market consumer product within 4 centuries. The tobacco industry in the 20th century then spent decades and billions of dollars suppressing the evidence that cigarettes caused cancer, evidence their own scientists had compiled internally. They marketed cigarettes to children. They hired doctors to endorse their products. They added chemical compounds specifically to make nicotine hit faster and harder, and leave the system more quickly, maximizing addiction. They turned something ancient and ritualistic and communal into a product specifically engineered to be as physically destructive and as financially extractive as possible. A shaman and a tobacco executive both worked with the same plant. They had almost nothing else in common. The gap between a shaman in 500 BC placing cannabis on hot stones in a ritual burial and a tobacco company executive in 1960 signing off on marketing cigarettes to teenagers is one of the larger moral chasms in human history. Both involve smoke. Almost nothing else is the same. So, when did ancient humans start smoking? The honest answer is, we don't know exactly. And we probably never will. The physical evidence takes us back 12,000 years with some confidence, and possibly much further with reasonable speculation. The behavioral drive that underlies smoking, the desire to alter consciousness, to share ritual experiences, to use inhaled substances as medicine, is almost certainly far older than any artifact we've found. It may be as old as fire itself. It may be as old as the cognitive leap that made us human in the first place. The ability to connect cause and effect, to look at a burning plant and think, last time that happened, I felt different. Let me do that again. That's not addiction, that's intelligence. What we do know is this: the behavior is extraordinarily old. It predates agriculture. It predates pottery. It predates every civilization you've ever learned about in school. What is absolutely clear is that by the time the historical record begins in every corner of the world where humans lived, they were already finding ways to put smoke into their bodies. The specific plants changed, the rituals changed, the purposes changed, but the behavior was already ancient by the time anyone thought to write it down. There's something almost poetic about that. For all the things that separate modern humans from our ancestors, the technology, the medicine, the internet, the truly baffling amount of content we consume every day, there are these thin threads of continuity that run unbroken through 100,000 years of human experience. Fire, smoke, breath. The oldest humans sat around fires and breathed the same smoky air you'd smell at a bonfire tonight. Some of them, at some point, started paying attention to what that smoke was doing to them. And then they started choosing it. And then they started passing that choice down to their children and their children's children, and eventually to the Scythians howling with pleasure in their tents, and the Egyptian physicians prescribing henbane, and the Mayan shamans reading visions in the rising smoke, and the Taino people on a Caribbean beach watching confused Europeans try tobacco for the first time and cough until their eyes watered. Either way, next time you flip a light switch, or sit around a Essie, summer fire, or catch a whiff of wood smoke on a cold night, you're participating in something far older than you realize. You're doing what humans have always done. You're breathing. In the 9th century, somewhere in the mountains of Sichuan or Shanxi province in China, a group of Taoist alchemists were trying to do something that had absolutely nothing to do with warfare. They were trying to live forever. Convinced that the right combination of minerals could produce an elixir of immortality, they spent years mixing, heating, and experimenting with whatever substances they could get their hands on, following recipes passed down through generations of mystical and medicinal tradition. At some point, one particular batch combined 3 ingredients: salt, peter, charcoal, and sulfur. And instead of granting eternal life, that mixture did something considerably more dramatic. It exploded. There are accounts of singed beards and burned-down workshops scattered through the early historical record, which tells you everything you need to know about how that first encounter actually went. Nobody in that room was trying to invent a weapon. They called the resulting substance huo yao, meaning fire medicine, a name that still carries the faint, slightly embarrassing memory of its original purpose as a failed pharmaceutical rather than a future engine of conquest. And yet that one accidental beard-singing batch of failed immortality medicine eventually became the single most consequential chemical discovery in the history of human conflict, the seed from which every gun, every cannon, and eventually every firearm on Earth would grow. So how did humans get from a failed potion in a Taoist alchemy lab to the firearm? The answer takes us through bamboo tubes strapped to spears. A siege that proved the new technology actually worked. Several centuries of careful refinement and a slow, steady migration of knowledge across an entire continent that eventually reshaped the balance of power on every inhabited landmass on Earth. Let's start with what that early gunpowder mixture actually was in the simplest possible term, because understanding the basic chemistry helps explain why everything that followed happened the way it did. The mixture those alchemists stumbled onto combined potassium nitrate known as saltpeter with charcoal and sulfur in roughly a 75 to 15 to 10 ratio by weight. The saltpeter functioned as an oxidizer, meaning it released oxygen rapidly when heated, feeding an extremely fast combustion reaction that produced a sudden, violent expansion of gas. That expanding gas is the entire secret behind everything gunpowder would eventually be used for, whether that meant launching fireworks into the night sky or eventually launching a metal projectile out of a tube with enough force to punch through armor. In its earliest documented uses, gunpowder wasn't weaponized at all. It was used for fireworks, smoke signals, and festival entertainment. Exactly the kind of celebratory decorative application you'd expect from something originally discovered by monks chasing immortality rather than military engineers chasing battlefield advantage. For generations, ordinary people across China encountered this substance primarily as spectacle rather than threat, lighting up festivals and religious ceremonies with bursts of color and noise that had nothing to do with combat at all. That changed once military commanders during the Song dynasty got a look at what this volatile new substance could actually do. Between the 10th and 12th centuries, Chinese engineers developed something called the Hiao Cheng, or fire lance, and the design was genuinely about as simple as a weapon could possibly be. Take a length of bamboo, strap it firmly to the end of a spear, pack the tube with gunpowder, and light it during close combat. The result was a polearm that spewed flame and burning debris directly at anyone within arm's reach, turning an ordinary spear into something considerably more terrifying to face in a melee. Defenders used fire lances during the siege of Dayan in 1132 against attacking forces climbing their walls. And by every account, the weapon worked exactly as intended, scorching and disorienting attackers in a way conventional spears simply couldn't match. The psychological effect alone was significant. Soldiers who had spent their entire lives training to fight with blades and spears suddenly found themselves facing an enemy who could project fire itself. And that kind of shock often mattered as much on a medieval battlefield as the actual physical damage inflicted. Once gunpowder had proven itself useful in actual combat, the pace of innovation accelerated quickly, and each successive improvement followed a fairly logical, almost obvious next step from whatever came before it. Makers of fire lances began stuffing pellets and shards of pottery into the bamboo tubes alongside the gunpowder, transforming a weapon that simply produced flame into one that also flung small projectiles outward with real force. This was a genuinely significant conceptual leap because it shifted the weapon's purpose from pure intimidation and burning toward actual physical penetrating injury delivered at a distance, the foundational concept underlying every firearm that would eventually follow. The next major limitation was the bamboo itself, which simply couldn't handle the pressure that more powerful gunpowder charges generated without splitting or bursting apart in the user's own hands, occasionally injuring the very soldier wielding it. Once Chinese craftsmen learned to cast bronze tubes strong enough to contain that pressure safely, the hand cannon was born. A weapon that used the expanding gas from gunpowder combustion to launch a single solid projectile with considerably more force and considerably more range than any bamboo fire lance ever could. By the 13th century, metal-barreled hand cannons were already in regular use across China, representing a genuine technological leap in both reliability and effectiveness compared to the earlier bamboo-based weapons. Chinese engineers also scaled the same basic concept upward, producing devices with names like the Thunderclap Bomb and the Heaven-Shaking Cannon, weapons capable of delivering genuinely high-impact explosions on a battlefield and reducing fortified positions that had previously seemed unassailable. When the Mongols invaded China in the 1200s, they encountered these gunpowder weapons firsthand during sieges like the famous defense of Qiong in 1232, and the experience left a lasting impression. Rather than simply being defeated by the new technology, the Mongols absorbed it, and once they had conquered China and established the Yuan dynasty, they carried gunpowder weaponry with them as they pushed westward into new conquests across Asia and toward the Islamic world. This is genuinely one of history's more important and underappreciated technology transfers because Mongol military campaigns functioned almost like an accidental delivery system, carrying gunpowder knowledge across enormous distances far faster than trade caravans or diplomatic exchanges ever could have managed on their own, spreading a Chinese invention across the breadth of Eurasia within the span of just a few generations. It's also worth noting that gunpowder weapons didn't develop along a single straight line during this period. Alongside hand cannons and fire lances, Chinese military engineers also developed rockets and fire arrows. Gunpowder propelled projectiles that found use not just in China, but eventually in Korea and India as well, traveling along separate but overlapping routes from the hand cannon's own path westward. These rocket weapons never fully disappeared the way the fire lance eventually did once true guns matured. Instead, they persisted as a distinct branch of gunpowder technology, one that would resurface centuries later in European warfare. And much later still, in the earliest ancestors of modern military and space rocketry, the story of gunpowder, in other words, doesn't just lead to the gun. It branches with one path heading toward the firearm and an entirely separate path heading toward the rocket, both rooted in the same accidental discovery made by alchemists who wanted nothing to do with either outcome. From there, gunpowder technology spread outward along multiple overlapping routes simultaneously, reaching the Islamic world and eventually Europe through a combination of military contact, trade, and the broader wave of cross-cultural exchange that characterized the 13th and 14th centuries. Historians studying this period point to a broader pattern worth appreciating. Gunpowder wasn't the only major Chinese invention making its way westward during this era. Paper, printing, and the magnetic compass all traveled the same general routes during roughly the same stretch of centuries, part of a much larger flow of technology and knowledge moving from east to west long before anyone had coined the term globalization. Some historians have noted that early European cannons bear such a close structural resemblance to Chinese designs that a direct transfer of knowledge seems considerably more plausible than independent invention happening to arrive at nearly identical solutions by coincidence. Once the technology reached Europe in the late 13th century, it landed in a political and military landscape that gunpowder weapons would, over the following centuries, completely and permanently transform, eventually dismantling systems of feudal military power that had stood for hundreds of years. The transformation wasn't instant. Early European hand cannons, much like their Chinese predecessors, were crude, slow to reload, and difficult to aim with any real precision. Essentially, a small cannon mounted awkwardly on the end of a pole, you loaded powder and projectile into the open end, touched a smoldering ember or a length of slow-burning cord to a small touch hole, and hoped with considerably more optimism than confidence that the resulting explosion would actually send the projectile somewhere useful. But even in this primitive form, the weapon carried a psychological and practical impact that traditional melee weapons simply couldn't match. Castle walls that had withstood traditional siege equipment for generations began falling to cannon fire. Mounted knights in heavy armor, the dominant military force across medieval Europe for centuries, found themselves increasingly vulnerable to a weapon that didn't care how much steel you were wearing, since enough gunpowder-driven force could punch straight through it regardless. The entire social and military order built around expensive, heavily armored cavalry began to wobble because a relatively cheap weapon in the hands of a far less expensively trained soldier could now neutralize an opponent who had spent a lifetime and a fortune preparing for combat in the traditional way. This shift had consequences far beyond the battlefield itself, reshaping the very architecture of European warfare. As cannons grew steadily more powerful and increasingly effective against vertical stone walls, traditional castle design built around tall, thin walls meant to repel scaling attackers, and arrows became dangerously obsolete almost overnight in historical terms. Military engineers responded by developing the star fort and the bastion. Lower, angled, thickly reinforced fortifications specifically designed to deflect and absorb cannon fire rather than simply standing tall and hoping for the best. The medieval castle, an architectural form that had dominated European landscapes for centuries, was gradually replaced by structures that looked almost nothing like it, all because of a weapon that had originated half a world away in the hands of monks chasing immortality. The next genuinely important leap came in the late 15th century with the invention of the matchlock mechanism. And this single development is what finally turned gunpowder weapons from clumsy novelties into the backbone of organized infantry warfare across the continent. The fundamental problem with earlier hand cannons was that actually firing one required two hands and considerable coordination. One hand to steady the weapon, the other to apply a burning ember or cord directly to the touch hole at exactly the right moment, all while trying to actually aim at a moving target on a chaotic battlefield. The matchlock mechanism solved this elegantly, by attaching a slow burning cord held in a curved clamp called a serpentine directly to the weapon itself. Pulling the trigger lowered that already burning cord directly into a small pan of priming powder, igniting the main charge automatically and freeing the shooter to actually hold and aim the weapon with both hands right up until the moment of firing. This may sound like a modest mechanical tweak, but it was genuinely transformative because it was the first mechanical firing device ever applied to a small arm. And it allowed for the first time in history a single trained soldier to fire a gunpowder weapon with some real degree of aimed precision, rather than simply pointing roughly in the right direction and hoping for the best. By the early 15th century, matchlock Arabuses were appearing in growing numbers across Western Europe, particularly in Spain, France, and the territories of the Holy Roman Empire, and the weapons spread rapidly from there across the entire breadth of Eurasia. The Ottoman Empire already experienced with gunpowder weaponry since the 14th century incorporated matchlocks directly into the elite Janissary Corps that formed the backbone of Ottoman military power, using the weapon to great effect in engagements such as the Battle of Goa in 1510, alongside the Portuguese forces that also relied heavily on matchlock weaponry during that same period. In 1543, Portuguese traders introduced matchlock technology to Japan, where local gunsmiths refined the design so thoroughly that Japanese matchlocks known as Tanegashima came to be regarded as some of the finest crafted firearms anywhere in the world during that period, prized for their precision and craftsmanship even by European observers. China itself, having started this entire chain of innovation centuries earlier, ended up reabsorbing an improved version of its own original invention, developing matchlock weapons known as birding guns, specifically to counter ongoing Mongol incursions along its northern frontier. A genuinely strange and fitting historical loop for a technology that began as a failed immortality potion in that same general region. Matchlock muskets eventually became heavy, powerful enough to need a forked rest just to support the barrel while aiming, weighing as much as 25 pounds in some configurations, but capable of punching through plate armor at ranges that made traditional swords and pikes increasingly irrelevant on an open battlefield. Because reloading and firing a matchlock took considerable time, and because the weapon left the user briefly vulnerable during that process, musketeers typically required protection from melee attacks, usually provided by pikemen standing alongside them. This combination of pikes and shot came to dominate European battlefields from the 16th into the early 17th century. An elaborate, carefully choreographed tactical system requiring extensive training to coordinate effectively with musketeers firing from behind or between rows of pikemen in tightly organized formations. Outside Europe, many armies that had adopted matchlocks retained their traditional formations rather than developing this same dense, disciplined infantry coordination, lacking either the resources or the specific tactical incentives that drove European armies toward this particular evolution in organized combined arms warfare. The matchlock had one obvious persistent weakness that everyone using it understood immediately. It required an open, slow, burning flame at all times, which made it nearly useless in wet weather, gave away a soldier's position in darkness, and required constant management of burning cord, even when nothing was happening on the battlefield at all. The solution arrived gradually through several intermediate steps worth understanding. The wheel lock, developed in the early 16th century, used a spring-loaded wheel spinning rapidly against a piece of pyite to generate sparks, eliminating the need for a constantly burning match entirely. Even as wealthier cavalrymen rode with the more advanced alternative, the true breakthrough came with the flintlock. Generally credited to French gunsmith Morin Lab Bourgeois, who developed the mechanism in its recognizable modern form around 1610 to 1615. The flintlock used a spring-loaded hammer holding a piece of flint, which struck a steel surface called a frisson to generate sparks directly into the priming pan, igniting the charge. It was faster to operate than a matchlock, dramatically more reliable in poor weather, and required no open flame to maintain at all, which also meant soldiers no longer gave away their position in the dark simply by carrying a lit weapon. By the 1630s, the flint-lock mechanism had spread rapidly across Europe, with the Dutch States Army among the first to formally adopt it as a standard-issue infantry weapon. And within a few decades, it had become the dominant firearm mechanism across essentially every major European military, a position it would hold for roughly 2 centuries, right through the colonial expansion, the Napoleonic Wars, and the American Revolution that followed, where flint-lock muskets carried by both colonial militias and British regulars defined the entire conflict from start to finish. The flintlock's arrival coincided with another genuinely important innovation, the socket bayonet introduced in the late 17th century, which attached around the outside of the barrel via a metal ring rather than plugging directly into the muzzle the way earlier plug bayonet designs had, which rendered the gun unable to fire while the bayonet was actually attached. This seemingly small change meant a soldier could fix a bayonet to his musket and still fire it normally, combining ranged firepower and close combat capability in a single weapon for the first time. The practical effect was enormous. Armies no longer needed dedicated pikemen standing alongside their musketeers for protection, since every soldier carrying a flintlock and bayonet could now function as both shooter and spearman, depending on what the moment required. This single combined development, sometimes called the Infantry Revolution, simplified training, simplified logistics, and fundamentally reshaped how European armies organized themselves on the battlefield, allowing regiments to become more versatile and capable of engaging enemies at range or in close combat without needing to reorganize entirely between the two modes of fighting. The bayonet charge also carried its own distinct psychological weight on the battlefield, since the sight of an advancing line of soldiers with fixed bayonets often broke enemy morale before a single shot or thrust ever actually connected. The flintlock's roughly 2-century reign finally ended in the early 19th century with the arrival of the percussion cap system, a small metal cap containing a shock-sensitive chemical compound that ignited instantly when struck by a hammer, eliminating the need for loose priming powder, flint, and cinta. This final ignition innovation rendered every previous mechanism, matchlock, wheel lock, and flintlock alike, essentially obsolete within a few decades, and it marked the last major milestone in the centuries-long chain of refinements that had begun with monks chasing immortality in 9th century China. From there, the pace of change only accelerated, leading toward repeating rifles, rapid advances in metallurgy and manufacturing, and eventually weapons that would have been utterly unrecognizable to the soldiers who once stood in disciplined lines with pikes and matchlocks waiting for their turn to fire. Looking back across this entire arc, from a Taoist alchemy lab in 9th century China to flintlock muskets dominating European battlefields nearly 8 centuries later, the story of how humans invented guns is really a story about accident, accumulation, and migration happening together over an enormous span of time. Nobody set out on day one to invent the firearm. A group of monks looking for immortality stumbled onto an explosive chemical reaction and very nearly burned their own beards off in the process. Military engineers watching that explosive reaction gradually realized its violence could be channeled, first through a tube strapped to a spear, then through a cast bronze cylinder, then through increasingly sophisticated mechanical systems designed to ignite that same basic chemical reaction more reliably, more quickly, and with less risk to the person holding the weapon. Each individual improvement, the shift from bamboo to bronze, from open flame to spring-loaded mechanism, from matchlock to flintlock, addressed a specific practical problem that soldiers and engineers had actually encountered using the version that came before it. None of it required some singular genius moment of total invention. It required centuries of incremental refinement carried across continents by trade routes, military campaigns, and the kind of slow cultural exchange that quietly reshapes the world while nobody's watching closely enough to notice it happening in real time. Passing hands between Chinese engineers, Mongol conquerors, Ottoman janissaries, Japanese gunsmiths, and European craftsmen, each group adding their own refinements along the way. The gun that would eventually end the dominance of mounted knights, reshape castle architecture, and ultimately determined the outcome of colonial conquests and continental wars across multiple centuries, began its existence as a mistake, made by people who were never trying to build a weapon at all. Picture this. A fisherman is out on a quiet stretch of water minding his own business when a wild dolphin suddenly appears next to his boat, nudging something toward him. He leans over expecting maybe a fish, maybe trash, maybe nothing at all. Instead, it's a baby dolphin tangled in fishing line, barely breathing. The mother is right there circling, watching, somehow understanding that this particular ape in this particular floating object might be able to help in a way she physically cannot. This isn't some isolated feel-good viral fluke either. This exact pattern, animals bringing their most vulnerable, most precious offspring directly to humans, shows up again and again across completely unrelated species on every continent in situations that have absolutely nothing to do with each other. And once you start pulling at that thread, the explanation gets a lot more interesting than animals just like us. Let's start with the obvious question, the one you're probably already asking. Why would any wild animal, a creature whose entire evolutionary programming is built around fear, suspicion, and self-preservation, voluntarily walk up to the single most dangerous species on the planet and hand over its baby? Humans have spent the last 10,000 years hunting, displacing, and occasionally domesticating basically every animal we've come into contact with. By every reasonable evolutionary metric, animals should treat us the way you'd treat a stranger holding a chainsaw at 2 a.m. And yet, over and over across species that share almost nothing in common biologically, we see the exact opposite. We see trust. Specifically trust at the moment it matters most when a life is on the line. So, let's actually dig into this because the answer isn't one single tidy explanation. It's a stack of overlapping reasons, and honestly, by the end of this, you might start side-eyeing your pets a little differently. First, let's talk about the cat thing, because if you own a cat, you might have already experienced this firsthand, and not even realized what was happening. Outdoor cats and feral cat colonies have a long, well-documented history of bringing kittens, sometimes injured, sometimes just newborn and helpless, directly to specific humans they've identified as reliable. Not random humans, specific ones. The neighbor who leaves food out, the person who once helped a stray with a thorn in its paw 3 months ago and was apparently never forgiven for it because now there's a steady stream of kittens showing up on the porch like some kind of furry subscription service nobody signed up for. Cats are incredibly good at building what researchers sometimes call a mental map of safe versus unsafe entities in their environment. They watch, they remember, they notice which humans are calm, predictable, and food-providing versus which humans are loud, erratic, or prone to chasing them off with a broom. Once a cat builds enough trust in a particular human, that human essentially gets reclassified mentally from potential threat to something closer to extension of the colony. And once you're inside that mental category, you start getting access to the same protective instincts a mother cat would extend to another trusted adult cat. The kittens get brought to you not because the cat thinks you're magic, but because you've already passed a months-long, completely unspoken background check. Now, here's where it gets stranger, because this same pattern of test, evaluate, trust, then deploy. The baby shows up in animals that are nowhere near as domesticated as your average backyard cat colony. Dolphins and whales have an extensive, well-documented history of approaching boats specifically when an injured calf or an entangled juvenile is involved. There's something almost eerie about how deliberate this behavior looks. These aren't panicked random encounters. Researchers and fishermen have reported cases where a mother whale will position an injured calf directly alongside a boat, hold position, and wait. Almost like she's saying, "All right, your turn. Do the thing you do." Marine biologists have pointed to cetacean intelligence and social complexity as a likely explanation here. Dolphins and whales already operate within incredibly tight-knit pods that practice cooperative care, shared babysitting duties, and coordinated rescue behavior among their own kind. If you already have the cognitive and social wiring to recognize this, individual needs help, and that other individual over there has the ability to provide it. It's apparently not that big a leap to occasionally extend that recognition across species lines, especially toward a species that's been floating around in slow, loud, clearly non-threatening boats for generations. There's also a sneaky little detail that gets overlooked here. Human boats are loud, but human distress responses are remarkably consistent and remarkably gentle when an animal is visibly injured or in trouble. Slow movements, quiet voices, careful hands. Animals are extremely good at reading body language, and a species that consistently responds to vulnerability with gentleness instead of aggression eventually gets filed under a different category entirely. We're loud, and we're everywhere, sure, but we're also weirdly one of the only species on the planet that regularly goes out of its way to help baby animals that aren't even our own. That reputation apparently travels. Let's talk about birds for a second, because bird behavior around humans gets wildly underrated in this whole conversation. There are well-documented cases of wild birds, magpies, crows, even certain raptors bringing injured or abandoned chicks towards specific humans who've previously shown some kind of caretaking behavior, feeding the local flock, rescuing a chick that fell from a nest, that sort of thing. Crows in particular are famous for this, mostly because crows have memory systems that would honestly embarrass some humans. Crows can recognize individual human faces for years, hold what looks suspiciously like a grudge against people who've wronged them, and extend something that looks a whole lot like loyalty toward people who've helped them. If a crow decides you're one of the good ones, that designation can apparently last basically forever, passed down even to the crow's own offspring, who somehow seem to know which humans are fine before ever directly interacting with them. This raises a genuinely fascinating possibility that some of this baby-delivering behavior isn't just individual trust, it's something closer to inherited or socially transmitted trust. A young animal raised around a parent who treats a particular human as safe may simply absorb that assessment the same way a human kid absorbs which neighbors are the nice ones without ever being explicitly told. Now, here's a big one that ties a lot of this together. Domestication didn't just change animals physically, it fundamentally rewired how certain species process trust and dependency in the first place. Dogs are the most obvious example here, and dog behavior around bringing puppies to humans is honestly one of the most touching things in the entire animal kingdom. A mother dog who trusts her owner will frequently bring newborn puppies directly to that person, sometimes literally carrying them one by one and depositing them at the human's feet like she's making a delivery. This isn't random. Domesticated dogs have spent roughly 15,000 years evolving alongside humans, specifically around cooperative care, shared resources, and mutual protection. Somewhere deep in dog psychology, humans got permanently filed under pack member with thumbs, and pack members get access to the puppies. It's not a fluke, it's the entire point of how the relationship evolved in the first place. And this is where the story gets a little bit deeper, because that same wiring, the stuff that makes a dog trust a human enough to hand over puppies, seems to occasionally bleed outward into wild populations too. There have been documented cases of wild wolves, coyotes, and even foxes showing unusually low fear behavior around specific humans in areas with long histories of indirect coexistence, feeding stations, low hunting pressure, generations of non-threatening encounters. It's not domestication exactly, but it's something adjacent to it. A kind of soft, slow-building familiarity that occasionally produces behavior you'd normally only expect from a fully domesticated animal. Let's get into elephants for a second, because elephant behavior around humans might be the single most emotionally devastating example in this entire topic. And I say that with full awareness that I'm explaining all this with a slightly goofy tone. Elephants have an enormous memory, famously enormous, and they form deep multi-generational social bonds within their herds. There are numerous documented cases of elephant herds approaching specific humans, often conservationists, rangers, or sanctuary workers with injured or orphaned calves, almost like they're requesting medical intervention. In several well-documented sanctuary situations, elephant mothers have been observed essentially presenting an injured calf to caretakers, standing back and waiting, sometimes for hours, clearly anticipating some kind of help. What makes this especially wild is that elephants appear to remember specific individual humans who've helped them or their herd members in the past, sometimes for years, sometimes for the animal's entire lifetime. There are stories of elephants recognizing former caretakers after a decade of separation, responding with behavior that looks an awful lot like genuine emotional recognition. If an elephant can hold on to a positive memory of a specific human for 10 plus years, it's honestly not that surprising that the same elephant would eventually decide that human is a safe option when a calf needs help. So, at this point, you might be noticing a pattern building here, and it's worth naming directly. Nearly every example we've covered involves animals with unusually strong memory, social complexity, and some history, even an indirect one, of low-threat interaction with humans. This isn't random animal behavior. It's closer to a slow-building cross-species trust algorithm built case by case, generation by generation, memory by memory. There's also a less romantic, more practical layer to all of this, and it's worth talking about honestly instead of just leaning into the warm, fuzzy version. Sometimes bringing a baby to a human isn't really a deliberate, thoughtful gesture of trust. Sometimes it's closer to desperation. A mother animal facing a predator threat, a flooding den, an injury she physically cannot treat, may simply be drawn toward the nearest large, slow-moving, generally non-predatory shape in the area, which, awkwardly, often ends up being us. Humans are big, loud, and tend to smell like campfires, sunscreen, and questionable fast food decisions, none of which scream, "I am a threat to your baby," in the same way a genuine predator's scent would. In a moment of crisis, an animal's options narrow fast, and sometimes the trust to the human option isn't really trust at all. It's the absence of a worse alternative. But here's the thing, even desperation-based trust still requires the animal's brain to make a calculated risk assessment that we, historically, don't deserve. The fact that approach the human consistently beats out do literally anything else in moments of crisis still says something genuinely remarkable about how animals have recalibrated their threat models around us over time. We've apparently, despite our extremely mixed track record, ended up coded as a viable emergency option across an enormous range of unrelated species. That's not nothing. There's also a fascinating angle involving scent and chemical signaling that doesn't get talked about nearly enough. Humans produce a very specific, very recognizable chemical signature, somewhere between the smell of soap, sweat, food residue, and whatever laundry detergent happens to be popular that decade. Animals with strong scent-based memory, and that's most mammals, can apparently catalog specific human scent profiles the same way they'd catalog the scent of a known, safe member of their own group. Once a human's specific scent gets filed under safe, predictable, non-threatening, it can apparently stick around in an animal's memory for an absurdly long time, which helps explain why some of these baby-delivering moments happen with animals that have only had a handful of prior interactions with the human in question. Now, let's talk about something that ties this whole topic together in a way most people never consider. Humans are weirdly, almost suspiciously good at recognizing and responding to distress signals from completely unrelated species. There's actual research suggesting that the specific pitch, urgency, and rhythm of distress calls across many mammal species share enough structural similarity that humans instinctively respond to them, even when we've never heard that particular animal's call before. A crying human baby and a distressed puppy trigger remarkably similar instinctive responses in adult humans. Faster heart rate, immediate attention, an urge to investigate and help. Some researchers think this instinctive sensitivity to vulnerability might not be limited to recognizing our own species' babies. It might be a broader, somewhat leaky caretaking instinct that occasionally triggers for other species' young as well. If animals have, over generations, picked up on the fact that humans consistently respond to distress signals with help rather than aggression, that reputation becomes an evolutionary asset worth exploiting even across species lines. And honestly, this might be the most important piece of the entire puzzle. We're one of remarkably few species on the planet that regularly, voluntarily, and repeatedly intervenes to help offspring that aren't our own and aren't even our own species. Most predators in nature view another species' vulnerable young as, well, lunch. Humans, despite an admittedly rocky overall relationship with the natural world, have built up a surprisingly consistent reputation across multiple unrelated animal groups as the one species that tends to choose help over harm when a baby animal is in distress. That reputation, built slowly, inconsistently, imperfectly across thousands of individual interactions, seems to be exactly what's driving so much of this behavior. Let's talk about primates for a moment, because this is where things get almost uncomfortably close to home. There are documented cases of wild and semi-wild primates, chimpanzees, bonobos, even certain monkey species in areas with long-term research stations bringing injured or orphaned infants directly toward familiar human researchers. This isn't entirely surprising once you consider how closely primate social cognition mirrors our own. Primates already practice something researchers call alloparenting, where infants are cared for not just by their biological mother, but by a wider network of trusted group members, aunts, older siblings, sometimes even unrelated adults who've proven themselves reliable. Extending that same alloparenting logic toward a long-term, consistently non-threatening human observer isn't actually that big a cognitive leap. If a chimpanzee troop has spent years watching a particular researcher behave calmly, predictably, and helpfully, that researcher essentially gets absorbed into the troop's mental map of acceptable infant-adjacent adults, which is a wildly specific category to earn membership in, but apparently achievable with enough patience and zero sudden movements. There's an entire branch of research dedicated to something called the humanist safe haven hypothesis. And while that name sounds like it belongs in a fairly dry academic journal, the actual idea behind it is genuinely fascinating. The theory suggests that across multiple independently evolved social species, individual animals can form what's essentially an attachment-style relationship with specific humans, similar in structure, though obviously not in depth, to the attachment bond between a human infant and a caregiver. Animals that form this kind of bond don't just tolerate the human in question, they actively seek them out during moments of stress. The exact same way a frightened toddler runs toward a parent instead of away from danger in a random direction. If a wild animal has formed even a rough version of that bond with a specific human, bringing a vulnerable baby toward that person during a crisis stops looking strange at all. It starts looking like exactly what you'd expect from any creature seeking out its version of a safe haven. It's also worth mentioning just how consistently this pattern shows up specifically around moments of medical necessity, rather than just casual social bonding. Animals don't typically bring their babies to humans to hang out or socialize. They bring them when something is clearly, visibly wrong. An injury, an entanglement, a respiratory problem, a wound that needs cleaning. This detail matters because it suggests these animals aren't just comfortable around humans in a general sense. They're making something that looks suspiciously like a triage decision. They've identified a problem beyond their own capability to fix, and they've identified a specific entity in their environment that has, in the past, demonstrated some ability to fix exactly that kind of problem. That's not blind trust. That's something closer to outsourcing a task to a specialist, which is a frankly impressive cognitive maneuver for an animal that, biologically speaking, has every evolutionary reason to keep predators and strangers as far away from its vulnerable offspring as physically possible. It's worth pointing out that this trust isn't universal, and it's definitely not unconditional. Animals that have had consistently negative experiences with humans, hunted populations, heavily persecuted species, animals living in areas with high human conflict show none of this behavior. The baby delivering pattern shows up almost exclusively in populations with either a long history of low conflict coexistence, individual positive past experiences, or species with unusually strong memory and social cognition that allow them to make nuanced case-by-case judgments about specific humans rather than judging our species as a whole. In other words, animals aren't trusting humanity in general. They're trusting you specifically, the one who left food out, who moved slowly and quietly during a previous encounter, who didn't scream and run the last time something wild and unexpected showed up nearby. There's also something worth mentioning about how this behavior gets reinforced over time. Almost like a feedback loop. A human responds well to one distressed situation. The animal, or its social group, remembers that. Future generations within that group inherit a slightly lower baseline fear response toward humans in general or toward that specific human in particular. And the cycle continues, slowly building toward exactly the kind of behavior we're talking about. It's not magic. It's not animals secretly knowing we're good in some grand cosmic sense. It's small, accumulated, repeated evidence building case by case until a wild animal eventually looks at a human and concludes, yeah, this one's probably fine. Hand over the baby. So why do animals bring babies to humans? Not because we deserve some kind of universal trust from the animal kingdom. Our track record is honestly far too messy for that. It's because across an enormous range of species in an enormous range of situations, individual animals have built individual case files on individual humans. And some of us, enough of us, apparently keep papaces. Every slow, careful approach to an injured animal. Every bowl of food left out for a stray. Every gentle, quiet response to something wild and frightened becomes a tiny data point in an evolutionary ledger we don't even know we're contributing to. And every once in a while, when the stakes are highest, when a baby's life is on the line and a desperate parent is scanning the environment for literally any option that isn't certain death, that ledger gets cashed in and a human ends up holding a kitten, a calf, a chick, or a baby dolphin, wondering how on earth they ended up being the chosen one. Turns out, we didn't get chosen randomly at all. We got chosen because somewhere along the way, despite everything, we earned it. There's one last layer to this that almost never makes it into the conversation, and it might actually be the most quietly profound part of the entire thing. This behavior changes us too. Every documented case of an animal trusting a human enough to hand over its most vulnerable offspring tends to have a ripple effect on the human involved, and often on entire communities around them. Rangers who've experienced this firsthand frequently describe it as one of the most meaningful moments of their careers. A kind of confirmation that the slow, often thankless work of building trust with wild populations actually means something on the other end. Conservation programs have started actively studying these trust-based interactions, not just as cute anecdotes, but as legitimate indicators of ecosystem health and human-wildlife relationship quality in a given area. A wild population willing to approach humans during a crisis is often a population living somewhere with lower hunting pressure, lower habitat conflict, and a longer track record of coexistence rather than competition. In a strange way, these baby-delivering moments end up functioning as a kind of informal report card on how well humans in a given region have been behaving toward the local wildlife. And maybe that's the most useful way to think about this whole phenomenon. It's not really a story about animals being unexpectedly sentimental or magically trusting of humanity. It's a story about consequences, about every quiet, patient, non-threatening interaction slowly accumulating into something that eventually gets tested at the worst possible moment. When a parent has nowhere else to turn, and a baby's life is hanging in the balance. Every single time that test gets passed, it reinforces something fragile and valuable that took generations to build and could probably be undone in an afternoon of carelessness. So, the next time you hear about a dolphin nudging an injured calf toward a boat, or a stray cat parading kittens onto someone's porch, or an elephant herd standing patiently beside a calf waiting for help, don't just file it away as a wholesome animal video. File it away as proof that every once in a while, across an entire planet full of species that have every reason to fear us, we've somehow managed to convince a few of them that we're worth the risk. Look at your hand right now. Whatever shade it is, yeah, whether you're pale enough to be mistaken for a piece of paper or dark enough to absorb sunlight like a solar panel, that color didn't come from nowhere. It came from one of the longest, strangest, most dramatic makeovers in the history of life on Earth. And the wildest part, it wasn't random. It wasn't an accident. It wasn't some cosmic roll of the dice. It was a survival story, a slow-motion biological negotiation between your ancestors and the sun. And the sun, for the record, was absolutely not playing fair. But what happened? The answer involves vitamin D, cancer, folate, Africa, ice ages, ancient farmers who accidentally rewired their own evolution, and a surprisingly rude star sitting 93 million miles away from us that caused all of this and has absolutely no regrets. If you trace the human family tree all the way back, every single one of your ancestors, regardless of where you're from today, had dark skin. Every single one. Not most of them, not the majority, all of them. Around 300,000 years ago, when Homo sapiens first appeared in Africa, the entire species was dark-skinned. There were no pale people. There were no fair-skinned populations anywhere on the planet. The concept of light skin didn't even exist yet in humans. Now, think about that for a second. Every person you've ever seen in a history book, every ancient civilization, every mythology, every cave painting, all of it traces back to a single founding population that looked nothing like a significant chunk of the modern human species. Which means at some point in history, something happened. Something changed. And that change was so powerful, so deeply embedded into our DNA, that it reshaped the physical appearance of entire populations across multiple continents over tens of thousands of years. So, what was it? Well, before we get to that, we need to understand something about skin itself, because most people have absolutely no idea what skin actually is or what it's actually doing for you right this second. A lot of people treat skin like it's just packaging, like it's the bag your body came in, the wrapping that holds your organs together while you walk around arguing with strangers on the internet. But skin is an organ, your largest organ, in fact. And it's doing about 47 different jobs simultaneously, most of which you never think about and never thank it for. One of those jobs, arguably one of the most important, is protection from UV radiation. UV radiation is the invisible energy the sun fires at Earth constantly and relentlessly, and it is not your friend. UV light breaks chemical bonds, it damages DNA. It causes mutations in your cells. And if those mutations pile up in the wrong places over enough time, they turn into cancer. Specifically, melanoma, one of the most aggressive forms of skin cancer in existence. Now, here's where skin color becomes relevant. The pigment that gives skin its color is called melanin. And melanin is, in the most literal biological sense, a sunscreen. A natural, built-in, always-on UV filter. The more melanin your skin contains, the darker it appears. And the more effectively it blocks UV radiation from penetrating into the deeper layers of tissue where your DNA lives. Dark skin isn't just a look, it's a shield. This is why in Africa, where our species originated, sitting directly under some of the most intense UV radiation on the entire planet, evolution selected hard and fast for dark skin. Having more melanin meant your DNA was better protected. It meant you were less likely to accumulate cancer-causing mutations. It meant you lived longer, stayed healthier, and, most importantly, from evolution's cold, calculating perspective, we're more likely to survive long enough to reproduce and pass your genes to the next generation. Natural selection is basically a very slow, very ruthless optimization algorithm. It doesn't care about aesthetics, it doesn't have opinions about beauty, it doesn't wake up in the morning with a vision for what the human species should look like. It runs one calculation over and over and over again, billions of times across billions of organisms. Does this trait help you survive long enough to have offspring? If yes, keep it. If no, eliminate it. In equatorial Africa, under that blazing sun, dark skin was a hard, emphatic yes. Every generation, every time. But here's the thing, and this is where the story gets genuinely, unexpectedly complicated. UV radiation doesn't just attack your skin cells, it also attacks something inside your body. Something small, invisible, and critically important. Something that, if you destroy it in the wrong person at the wrong moment, can end a pregnancy before it even really begins. The molecule in question is called folate. It's a form of vitamin B9, and it flows through your bloodstream doing essential biological maintenance work. Now, you might be thinking, okay, vitamin B sounds like something my doctor told me to eat more of. Why does this matter for skin color? It matters enormously, especially if you are pregnant or trying to become pregnant. Folate is critical for the development of the neural tube in embryos. The neural tube is the structure that eventually becomes the brain and spinal cord. Without sufficient folate in the first few weeks of pregnancy, sometimes before a woman even knows she's pregnant, the neural tube can fail to close properly. The consequences are catastrophic. Neural tube defects, severe developmental abnormalities, miscarriage. Now, here's the problem. UV radiation destroys folate. When UV light penetrates the skin and reaches the bloodstream, it breaks down folate molecules. And in a sun-drenched environment like equatorial Africa, with no clothing, no shelter, no sunscreen, UV exposure was constant, intense, and unavoidable. This created an additional, devastating selection pressure. Pregnant women with lighter skin, less melanin, more UV penetrating deeper, had higher rates of folate destruction. Higher rates of folate destruction meant higher rates of neural tube defects. Higher rates of neural tube defects meant fewer surviving offspring. So now we have not one, but two completely independent reasons why dark skin was deeply, powerfully, non-negotiably favored under the African sun. 1. Melanin protected DNA from UV damage, reducing cancer risk. 2. Melanin protected folate in pregnant women, preserving reproductive success. Two separate threats, one biological solution. Dark skin in Africa wasn't just useful, it was essentially mandatory for the survival of the species. Okay, so dark skin is this multi-purpose biological superweapon. It blocks cancer, it protects folate, it has been field tested and optimized over hundreds of thousands of years. If evolution had a review system, dark skin would have a 5-star rating with thousands of glowing testimonials. So why, in the name of everything logical, did it change? Why did populations that left Africa end up getting lighter and lighter over thousands of years? The answer is one of the most elegant, brutal trade-offs in all of evolutionary biology. Between roughly 70,000 and 100,000 years ago, groups of Homo sapiens began leaving Africa. It wasn't a single dramatic event. No one organized a meeting. No one announced a great migration. It was slow generational drift. A group moves a little further than their parents did. Their children move a little further still. Over thousands of years, humans spread through the Middle East, into Europe, across Asia, and eventually into the Americas. And as they moved north, something fundamental about their environment changed. The sun got weaker. Not the sun itself. The sun remained exactly as indifferent and nuclear as always, but at higher latitudes, sunlight hits Earth at a lower angle. It passes through more atmosphere before it reaches you. UV radiation is filtered out. Days are shorter, winters are long and dark. The sky is overcast for months. In Northern Europe, in Northern Asia, in Canada, the UV environment is radically, dramatically different from equatorial Africa. Instead of relentlessly intense radiation you need to block, you have weak, intermittent radiation you desperately need to absorb. And suddenly the dark skin that was perfect in Africa became a problem. Not because of cancer. The cancer risk at northern latitudes with weak UV was much lower. Not because of folate. Less UV meant less folate destruction. So that was fine. No, the problem was something different, something that doesn't get nearly enough credit in this story. Vitamin D. Vitamin D is synthesized in the skin when UVB radiation hits a compound called 7-dehydrocholesterol. Your skin is literally a solar panel. It uses sunlight as an energy source to manufacture this essential molecule. And vitamin D is not optional, not even a little bit. It is absolutely fundamental to human health. Vitamin D regulates calcium and phosphorus absorption in the gut. Without it, calcium doesn't get properly absorbed, no matter how much dairy you consume. Without calcium, bones don't mineralize correctly. In children, severe vitamin D deficiency causes rickets, a disease that softens and deforms the bones, bows the legs outward, causes the skull to flatten, and stunts growth. In adult women, vitamin D deficiency can cause a condition called osteomalacia, which softens the pelvic bones. And softer deformed pelvic bones make childbirth extraordinarily dangerous, sometimes impossible. Women with severe vitamin D deficiency had dramatically higher rates of death during labor. But vitamin D deficiency doesn't stop at the skeleton. It also impairs immune function, making you more susceptible to infections. It affects muscle strength. It influences cardiovascular health. Some research links chronic deficiency to depression and cognitive decline. Vitamin D does so much biological work that when you run out of it, the body starts failing in multiple systems simultaneously. Now, put a dark-skinned person in Northern Europe 40,000 years ago. They have highly efficient melanin. Their skin blocks UV radiation beautifully, which is brilliant in Africa. But in the gray, overcast, low-light north, that same melanin is now blocking the very UV they need to synthesize vitamin D. Their skin can't tell the difference between dangerous UV I should block and useful UV I desperately need. It just blocks. So they don't make enough vitamin D. Their calcium absorption drops, their bones weaken, their children develop rickets, women die in childbirth. The population starts declining. Dark skin in northern latitudes wasn't just a disadvantage. In a pre-industrial world with no supplements, no fortified food, no medical interventions, it was a death sentence stretched across generations. And evolution, that cold, merciless, endlessly patient calculator, started selecting against it. Mutations that reduced melanin production began appearing in the population, randomly, as mutations always do. But instead of being eliminated, they spread because individuals with slightly lighter skin synthesized slightly more vitamin D, had slightly healthier bones, had slightly higher reproductive success. Generation after generation, slightly lighter, slightly lighter, slightly lighter. Over thousands of years, the average skin tone of northern populations drifted upward. Not because anyone decided it should, not because of culture or preference or social forces, but because in that specific environment, at that specific latitude, with that specific amount of sunlight, lighter skin kept more people alive. The algorithm had simply reversed its inputs. For a long time, scientists assumed the depigmentation of European populations happened gradually over hundreds of thousands of years. A slow, steady evolutionary drift as people moved north. Recent ancient DNA analysis has completely demolished that assumption and replaced it with something far more interesting. Early European hunter-gatherers, the people who lived in Europe for tens of thousands of years after the initial migration out of Africa, were still significantly dark-skinned. Even after living at northern latitudes for a very long time, they hadn't dramatically depigmented. The most famous example is a specimen known as Cheddar Man. He lived in what is now Britain approximately 10,000 years ago. Ancient DNA analysis published in 2018 revealed he likely had dark to medium dark skin, dark curly hair, and blue eyes. A combination that looks almost paradoxical to modern eyes because we've come to associate blue eyes with very pale skin. But 10,000 years ago, that wasn't yet the case. The extremely fair skin we associate with Northwestern Europeans today, the kind that burns in about 12 minutes of summer sun, appears to have spread widely across European populations only in roughly the last 6,000 to 8,000 years. That is shockingly recent. In the full 300,000-year history of Homo sapiens, that's less than the last 3%. So, what happened 6,000 to 8,000 years ago that suddenly accelerated this process so dramatically? The answer is one of the biggest transitions in human history, and almost nobody talks about its effect on skin color. The Neolithic Revolution, the switch from hunting and gathering to farming. When humans transitioned to agriculture, their diet changed completely and permanently. Hunter-gatherers ate a varied diet that naturally included significant amounts of vitamin D. Fatty fish, like salmon and mackerel, organ meats like liver and kidney, shellfish, and other animal products that are among the richest dietary sources of vitamin D in existence. Farming populations ate mostly cereals, wheat, barley, oats, rye, carbohydrates. Their dietary vitamin D intake didn't just drop, it collapsed. Suddenly, populations that had been getting by with modest amounts of UV synthesized vitamin D because their diet was also contributing, were now almost entirely dependent on whatever their skin could produce, and if their skin was still fairly dark, that wasn't enough. The selection pressure for lighter skin intensified dramatically. Even tiny increases in vitamin D synthesis ability, even marginally less melanin, became critically important for survival. But there's a second factor that made this change happen faster. Farming communities were large. They were dense. They were sedentary. And population size and density have enormous effects on how quickly an advantageous mutation can spread through a gene pool. In a small scattered hunter-gatherer band of 50 people, a beneficial mutation might take a very long time to reach even neighboring groups. In a farming village of hundreds connected to a network of other farming villages, a beneficial mutation can spread through thousands of descendants in just a few generations. The combination dietary vitamin D collapse plus population density essentially hit the fast-forward button on European depigmentation. Within a few thousand years, the selective pressure that had been quietly nudging skin tones lighter for tens of millennia suddenly became intense, rapid, and visible in the archaeological record. Here's something that genuinely surprises most people when they first hear it. Skin color is not controlled by a single gene. There is no dark skin gene and light skin gene where one dominates the other. It's far more complicated than that. Skin pigmentation is a polygenic trait. It's controlled by dozens of different genes working together. Genes that influence how much melanin is produced, what type of melanin is made, how melanin granules are distributed inside skin cells, and how the skin responds to UV exposure over time. And here's what makes this truly remarkable. Different populations that independently evolved lighter skin did not use the same genes to do it. East Asians and Europeans both have significantly lighter skin than equatorial Africans. But the genetic variants responsible for lighter skin in East Asians are largely different from the variants responsible in Europeans. They arrived at similar outcomes through different molecular routes. This is called convergent evolution. The same adaptive solution, lighter skin in low UV environments, discovered independently through completely different genetic pathways by separate populations on separate continents. Think about what that means. The evolutionary pressure was so strong, so consistent, so unambiguous that natural selection found the same answer multiple times. Not once, Not twice, multiple times, independently. When evolution keeps reinventing something from scratch, that's as strong a signal as biology ever gives you that the trait in question really, really matters for survival. While we're in the genetic neighborhood, let's talk about something adjacent that is equally mind-bending: blue eyes. Every single person alive today with blue eyes, every single one, no exceptions, is descended from one specific individual. One person, one mutation, one moment somewhere around the Black Sea region, approximately 6,000 to 10,000 years ago. Before that individual was born, the entire human species had brown eyes. Everyone. Brown, brown, nothing but brown as far back as you go. Then this one mutation appeared, a change that reduced melanin production specifically in the iris. And it spread. Slowly at first, then faster, because it was probably genetically linked to skin pigmentation variants that were themselves under strong selection. Now consider something as seemingly ancient and fundamental as blue eyes. Something that has been used to sort humans into categories throughout history is younger than the invention of agriculture. It's younger than Stonehenge. It's younger than the domestication of the horse. We treat certain human traits as ancient and primordial when they are, in geological or even in terms, basically brand new. The version of humanity we think of as normal and, clears throat, fixed is still being written. Let's take a step back and look at the full picture. Skin color. The thing that has defined so much of human history, shaped political systems, justified atrocities, divided and sorted people into hierarchies for millennia, is, at its biological core, a UV calibration system. It is a dial, an adjustment mechanism. Your body's best ancestral estimate of how much sunlight protection you need, given the latitude your distant ancestors happened to inhabit, the diet they happened to eat, and the sun they happened to live under. Light skin isn't better in any absolute sense. In equatorial environments, it's actively dangerous. More UV penetration, more DNA damage, more cancer risk, more folate destruction. Light skin in Africa is a survival disadvantage. Dark skin isn't less evolved or primitive. It is the ancestral state, the original configuration, the baseline from which everything else is a modification. If anything, lighter skin is the newer version, the adaptation, the variation. Dark skin is the default, and the deepest irony of all is this. The same sun that drove some populations to develop more melanin to survive its power also drove other populations to develop less melanin because they needed more of its limited energy. The sun didn't pick sides. The sun didn't have preferences. The sun just radiated indifferently and let evolution sort out the rest. We built an entire civilization's worth of prejudice, oppression, and hierarchy around a vitamin D problem, a calcium absorption issue, a folate protection mechanism. Human populations are still evolving, slowly, almost imperceptibly on any individual timescale, but evolving nonetheless. The selection pressures that shaped skin color are still present in the environment, even if modern technology has partially muffled them. We have vitamin D supplements now. We have sunscreen. We have fortified foods and electric lighting and heated houses and year-round access to food from every latitude on Earth. We've built a civilization that partially decouples skin biology from its original function. The evolutionary algorithm is still running, but we've changed the inputs. What that means for the human species over the next 100,000 years, nobody can say. Evolution doesn't send newsletters, but what we can say with complete confidence is that every shade of human skin that exists today is the product of the same ancient population standing in the African sun, slowly spreading across an unpredictable planet, and carrying written in melanin the precise record of every environment their descendants passed through. Every skin tone is an answer to a question asked by a star, and every single answer was correct. You are a human baby. You cannot walk. You cannot talk. You cannot feed yourself. You cannot regulate your own body temperature. You have no idea what a predator is, but predators absolutely know what you are. You weigh about 3 kilograms. You are, to put it bluntly, a biological disaster waiting to happen. And yet somehow you have ancestors, thousands of generations of them, which means that somewhere at some point, a chain of ancient humans figured out how to keep something as catastrophically fragile as a newborn alive. Not for a day, not for a week, for long enough to make more babies over and over again for 300,000 years. So the question isn't just interesting, it's personal. Because if even one of your direct ancestors had failed at this, just once, you wouldn't be here watching this video right now. You'd simply not exist. That's a little unsettling when you think about it, but here's the wild part. The answer to how ancient humans kept children alive isn't just a list of old-fashioned survival tips. It's actually a window into some of the most sophisticated social behavior ever to evolve on this planet. Behavior that most people never think about. Behavior that, in many ways, we've quietly abandoned in the modern world and are now paying the price for. Let's start with the obvious question nobody asks. Why is human birth so difficult in the first place? Most animals come out running, or at least walking. A baby giraffe drops nearly 2 meters to the ground, lands, gets up, and starts trotting within an hour. A baby horse is on its feet in less than 2. Even our closest relatives, chimpanzees, are able to cling to their mother almost immediately after birth. Human babies? Absolutely not. A human newborn is helpless for months, completely and utterly dependent on other people for literally everything. And this isn't a coincidence or a design flaw. It's actually a very specific evolutionary trade-off with a name. Scientists call it secondary altriciality, which sounds like a made-up word, but it means something real. Human babies are born earlier relative to their development than almost any other primate. Why? Because of your brain. Here's the problem. Human brains are enormous, not just compared to other animals, even compared to what our bodies should theoretically support. A fully developed human brain at birth would require a skull so large that it simply could not pass through the birth canal. So evolution did something rather clever and slightly horrifying. It made us give birth early. Human babies are essentially born premature by design. At birth, your brain is only about 25% of its adult size. A chimpanzee baby is born at around 45%. This means that a huge amount of human brain development, the stuff that takes other animals weeks or a few months, takes us years. And all of that development has to happen outside the womb, completely exposed to the world, while the baby is entirely dependent on other people. This is sometimes called the obstetric dilemma, and it means something crucial. A human infant cannot survive alone, not even theoretically, not even for a few hours. The species quite literally cannot reproduce successfully without social support. And this changes everything, because it means that how did ancient humans keep children alive isn't really a question about individual skill. It's a question about collective behavior, about social systems, about the structure of groups, and what ancient humans came up with was honestly remarkable. You've heard the phrase, "it takes a village to raise a child." It's become a bit of a cliche at this point. People say it at baby showers. They put it on motivational posters. But here's what most people don't realize. In the context of early human evolution, it was not a metaphor. It was a literal biological strategy. And it was so effective that anthropologists believe it may be one of the main reasons Homo sapiens outcompeted every other hominin species on the planet. The theory is called cooperative breeding, and it goes something like this. In most primate species, child rearing is almost entirely the responsibility of the mother. The father occasionally helps, but the core burden falls on one individual. This limits how many offspring a mother can realistically have because she can only care for a limited number of dependent children at once. Humans broke this pattern dramatically. In hunter-gatherer societies, which represent the vast majority of human evolutionary history, childcare was distributed across the entire social group. Not as a favor, not as a cultural nicety, but as a fundamental part of how the group functioned. Grandmothers played an especially critical role, so much so that there's actually a dedicated scientific hypothesis about it called, you guessed it, the grandmother hypothesis. This theory, developed in the 1990s by anthropologist Kristen Hawkes, proposes that human menopause, which is itself extremely unusual in the animal kingdom, evolved specifically to allow older women to stop reproducing and instead invest energy into the survival of their grandchildren. Let that sink in for a second. The idea is that human females live for decades past their reproductive years precisely because experienced grandmothers are so valuable to child survival that evolution found it more efficient to have them stop having babies and start helping raise everyone else's. And the data actually supports this. Studies of traditional societies have found that the presence of a maternal grandmother significantly increases child survival rates. In some populations, it's one of the strongest predictors of whether a child lives past age 2. It wasn't just grandmothers either. Aunts, uncles, older siblings, unrelated adults within the group, all of these individuals participated in childcare in ways that simply don't happen in most primate societies. Young children were passed around, held, carried, fed, watched over by multiple adults throughout the day. Researchers who have studied modern hunter-gatherer groups, which give us at least some window into ancestral human behavior, report that in groups like the Aka of Central Africa, fathers are within arm's reach of their infants roughly 47% of the time. 47%. That's more involved than most fathers in industrialized societies today. The point being, the social architecture around ancient human children was extraordinarily dense. The child was embedded in a web of relationships not just dependent on two parents. This wasn't philosophy. It was survival engineering. Now, let's talk about something that tends to make modern audiences a bit uncomfortable. In ancient human societies, breastfeeding looked nothing like what we consider normal today. First, duration. In traditional societies, and among our closest primate relatives, breastfeeding typically continued for 2 to 4 years, sometimes longer. The World Health Organization currently recommends breastfeeding up to age 2 or beyond, which strikes many people as surprising. But from an evolutionary standpoint, weaning before 2 years would have been genuinely unusual and potentially dangerous. Second, frequency. Hunter-gatherer mothers typically breastfed their children multiple times per hour during the day. Some studies estimate as many as 4 times per hour in the early months. This constant feeding serves multiple purposes. It provides nutrition. It regulates the infant's stress response. And crucially, it acts as a natural contraceptive, suppressing ovulation and spacing births apart by roughly 3 to 4 years. That birth spacing matters enormously. One of the most consistent findings in studies of hunter-gatherer populations is that children are naturally spaced about 3 to 4 years apart. This is not an accident. It's the biological rhythm of a species where carrying and nursing one child to relative independence before having another was a matter of survival. But here's where it gets interesting. Wet nursing, that is breastfeeding someone else's child, appears to be extremely ancient and cross-cultural. Anthropological evidence suggests that in many societies, multiple women in a group would breastfeed children who weren't their own. This not only helped orphaned or ill children survive, but also strengthened social bonds between families in ways that may have had broader survival benefits. It was, in a very literal sense, a community resource. Let's think practically for a moment. You are a hunter-gatherer mother in the Pleistocene. You need to gather food, probably walking several kilometers a day over uneven terrain. You need to do this while keeping a completely helpless infant alive. How? You cannot put the baby down. Predators exist. Other dangers exist. The baby cannot regulate its own temperature. If it gets cold, it can die surprisingly quickly. And a crying baby left alone is a beacon to anything nearby that eats meat. The solution ancient humans arrived at was elegant and is now backed by extensive research. Constant physical contact, carrying infants against the body, what we now call baby wearing, appears to be the ancestral norm for our species. The evidence comes from multiple directions. Physiologically, human infants have a strong grasping reflex. When you touch the palm of a newborn, they grip instinctively with surprising force. This reflex, which is actually a remnant behavior, likely evolved for clinging to a caregiver. Neurologically, infant brain development is strongly optimized for close physical contact. Studies have shown that skin-to-skin contact regulates infants' heart rate, breathing, body temperature, and stress hormones. Infants who are carried more cry less. Not because they're spoiled, but because the contact is meeting a genuine biological need. Cross-cultural surveys have found that in societies where infants are carried throughout the day, infant crying is dramatically lower than in societies where babies spend significant time alone. Roughly 50% less by some estimates. The crying isn't a personality trait. It's a response to conditions that, from an evolutionary standpoint, signal danger. Ancient human infants were almost certainly carried for the majority of their waking hours. They slept in physical contact with caregivers. They were rarely, if ever, left alone. Modern parenting advice, by contrast, has spent much of the last century encouraging the opposite: cribs, separate rooms, schedules, sleep training. Some of this works fine, but it's worth knowing that we are, in historical terms, running a rather large and poorly controlled experiment on our own species. Eventually, at some point, the baby has to eat something other than milk, and this is where things get creative and occasionally disgusting. The introduction of solid foods in ancient societies was not what we'd recognize today. There were no pureed organic carrot pouches. There were no perfectly calibrated first foods. There was whatever the group had managed to find or kill that day, processed in whatever way was available. The most common method for softening food for infants across ancient and traditional societies was pre-mastication, adults chewing food and then transferring it to the infant's mouth. This sounds shocking by modern hygiene standards, and it is true that it transfers bacteria from adult to infant mouths. But here's the twist: some of those bacteria may actually be beneficial. Research has found that infants who receive pre-masticated food may be exposed to beneficial oral microbiota from their caregivers, potentially supporting immune development. It's also worth noting that among our primate relatives, chimpanzees regularly use pre-mastication. It appears to be an extremely ancient behavior, probably as old as our genus. Beyond pre-mastication, ancient children would have been given soft foods relatively early. Marrow from cracked bones, which is calorie-dense and easy to consume. Mashed plant foods, eggs, small pieces of fish or meat. The diet was remarkably varied. And research on ancient dental remains suggests that children in hunter-gatherer societies generally had better overall nutrition and fewer cavities than early agricultural populations who became heavily dependent on starchy grains. Yes, hunter-gatherer children had better teeth than Bronze Age children. Turns out that eating everything is healthier than eating mostly bread. Here is something nobody tells you about the ancestral human sleep environment. Nobody slept alone. We touched on this in another context, but it deserves its own section because it's so dramatically different from modern expectations. In every observed hunter-gatherer society, and in the vast majority of traditional cultures worldwide, infants and young children sleep in physical contact with at least one adult, not in a separate room, not in a crib, against a human body all night. This practice, called co-sleeping or bed sharing, is not a counterculture parenting choice. It is the default human behavior for roughly 99% of our species' existence. The arguments against it in modern Western medicine are rooted in very specific and real concerns, particularly the risk of accidental suffocation in soft bedding environments with impaired caregivers. These are legitimate concerns in specific modern contexts, but in ancestral environments, sleeping on firm surfaces with sober and responsive caregivers in relatively cool conditions, the same risks don't apply in the same way. And the benefits of co-sleeping for infant development are well documented: more stable body temperature, more regulated breathing, more frequent nighttime nursing, and significantly higher rates of breastfeeding duration. There's also an interesting theory about co-sleeping and SIDS, sudden infant death syndrome. Some researchers, including anthropologist James McKenna, who has spent decades studying infant sleep, have proposed that the normal stimulation provided by a sleeping adult's breathing and movement helps regulate an infant's own breathing patterns during a developmental window when that regulation is still unreliable. Whether or not that specific theory is fully proven, the broader point stands. Human infant physiology evolved expecting physical contact during sleep. The separate nursery is a very, very recent invention, and the infant mortality statistics for most of human history are sobering enough to suggest that for most of those years, something was working. Let's be honest about something. For most of human history, infant mortality was staggeringly high by modern standards. Best estimates suggest that in Paleolithic and early Neolithic populations, somewhere between 30% and 50% of children died before age 5. This is not because ancient humans didn't care, it's because they were operating without germ theory, without antibiotics, without vaccines, without modern nutrition science, without most of the things that have driven child mortality down by roughly 96% since 1800. They did what they could, and some of what they did was actually effective. Medicinal plant use appears to be ancient. Chimpanzees self-medicate with specific plants, and the archaeological record shows evidence of deliberate herb use going back at least 50,000 years. Many traditional societies developed sophisticated pharmacopoeias, collections of plant-based remedies, that we are still mining today for pharmaceutical leads. Willow bark, the original aspirin, has been used for pain and fever management for thousands of years. Honey was used as an antimicrobial wound treatment in ancient Egypt and likely much earlier. Garlic has genuine antimicrobial properties that ancient peoples had empirically identified long before they had any framework to explain why. None of this saved children from bacterial meningitis or severe dehydration, but it wasn't nothing. What also existed extensively and universally was ritual. Every human culture on record has developed ceremonies around birth and early childhood, naming rituals, protective charms, prayers, rites of passage. To a modern observer, these might seem like pure superstition, but anthropologists argue they served real social functions. They bound the community together around the child. They publicly assigned responsibility for the child's welfare. They provided psychological frameworks for processing grief when children inevitably died. There is evidence that the grief was real and profound. Infant burials in archaeological sites are often carefully arranged, sometimes with grave goods, sometimes with flowers. The idea that ancient humans were indifferent to their children's deaths, that life was so cheap that loss was shrugged off, is contradicted by the archaeological record at every turn. They mourned. They tried. And slowly, over thousands of years, they accumulated enough empirical knowledge to incrementally improve the odds. Here's the part of this video that nobody expects. A lot of what ancient humans did to keep children alive was more effective than what we replaced it with. Not all of it. Absolutely not all of it. Vaccines, clean water, modern medicine, these are not debatable. The collapse of child mortality in the 20th century is one of the greatest achievements in human history. Full stop. Nobody sensible is arguing we should go back to 40% child mortality. But within the domain of behavioral childcare, the social, emotional, and physical environment of early childhood, there's a compelling argument that industrialized societies have dismantled structures that were doing important work without fully understanding what we were dismantling. The extended family network that distributed childcare across multiple adults. In many Western countries, families are now nuclear at best, frequently scattered geographically, sometimes entirely isolated. The constant physical contact during the day replaced with bouncers, swings, and playpens. Devices explicitly designed to keep the baby content without being held. The communal sleep environment replaced with the separate nursery and a cultural anxiety around dependence that, from an evolutionary standpoint, is frankly a little strange. None of this is a moral failure. It's the product of specific economic and social changes. Urbanization, the two-income household, the collapse of extended family structures. These changes happened for reasons that had nothing to do with child welfare, and parents navigating them are doing their best. But the rates of postpartum depression, infant sleep disorders, and parental burnout in industrialized societies are real, documented, and remarkably high. And when you look at the social structure those parents are operating within and compare it to the social structure humans evolved in, the gap is enormous. The ancient answer to, how do you keep a child alive, was, you don't do it alone. You don't even primarily do it as a couple. You do it as a group. You share the load. You distribute the exhaustion. You make sure that no single adult is ever the sole point of failure in a child's survival. That's not a philosophy. That's engineering. So, how did ancient humans keep children alive? They carried them constantly. They breastfed them for years. They slept next to them every night. They chewed their food for them. They surrounded them with a web of attentive adults, grandmothers, aunts, uncles, neighbors, friends, all of whom took genuine responsibility for the child's welfare. They mourned when children died, which happened often. They tried to understand illness with the tools they had, which were limited. They developed rituals to hold communities together in the face of grief. They slowly accumulated knowledge across generations, passing it forward in the form of tradition, practice, and eventually, much later, writing. And the thread that runs through all of it, the thing that is most consistent across every culture, every time period, every geography is that children survived when they were embedded in social connection and struggled when they were isolated. That's not just ancient history. That's still true. We've built extraordinary technology for keeping children physically safe. We've made remarkable progress on the biological threats that once killed half of all children before they could walk to school. That is genuinely profoundly good. But the social technology, the dense, overlapping, distributed network, that's the part we're still figuring out how to preserve. The ancient humans didn't have antibiotics. They didn't have ultrasounds. They didn't have formula or pediatricians or car seats. What they had was each other. Really matter. That was enough. Imagine you haven't eaten in 2 days. You know exactly where the herd is. You tracked it yesterday. You found the prints. You mapped the route in your head. And now all you have to do is get there. And then it starts raining. Not a light drizzle, a heavy soaking wind-driven rain that doesn't stop. It goes all day, then all night. Then the next morning, and it's still going. So now you can't hunt. You can't see tracks because the mud's washed them away. You can't move through the open because wet ground and bare feet on rocky terrain means a twisted ankle. And a twisted ankle out here means death. The river near your camp is rising. And the fire, the one thing keeping you warm, keeping predators away, and keeping you alive, is now starting to struggle. You're not bored. You're trapped. For most of human history, rain wasn't an inconvenience. It was a crisis, and what ancient humans did during that crisis might be more important than anything they did on a clear day. Today when it rains, you close your window, make some coffee, maybe grab a blanket and open Netflix. You get cozy on the couch, start wiggling into that perfect spot, and just sink in. For you, rain is just background noise. It makes you feel calm, makes you feel sleepy. You might not even make it through the episode. But for a human being 50,000 years ago, that same rain, the exact same sound you're falling asleep to, could kill you in 3 different ways before it even stopped. The first one is cold. A wet human loses body heat up to 25 times faster than a dry one. Without clothing, without waterproof shelter, a long rainstorm in anything below about 50 degrees Fahrenheit could drop your core temperature into hypothermia range within hours. And most of the world our ancestors lived in got that cold at night, even in Africa during the wet season at higher elevations. The second one is flooding, caves and rock shelters. The main places humans lived are often at the base of hillsides or near rivers. So, heavy rain meant flash floods. Archaeologists have found layers of flood sediment inside occupied caves, meaning the water came in while people were living there. Some of those layers are thick, and they found out that those caves were never used again. And the third one, maybe the worst, is predators. Rain drove animals into shelter too, and sometimes that shelter was the same cave you were in. There are cave sites in South Africa where human remains and large cat remains are found in the same layers. Some of those humans have puncture marks in their skulls that match leopard teeth perfectly. So rain didn't just make life uncomfortable. It compressed the entire world. Humans, predators, prey, all of them squeezed into the same small, dry spaces at the same time. And in the middle of all that, one job mattered more than everything else: keeping the fire going. And here's why that was so terrifying. Before roughly 40,000 years ago, we're not entirely sure how reliably humans could start fire from scratch. There's evidence of controlled fire use going back at least 400,000 years at a site called Kusum Cave in Israel, and possibly as far back as 1,000,000 years at Wonderwork Cave in South Africa. But here's the thing: controlling a fire that already exists and creating one from nothing are 2 very different skills. And for most of human history, most people probably couldn't do the second one. So if your fire went out, you might not be able to relight it. You'd have to carry an ember from somewhere else, which some groups actually did. They transported smoldering coals wrapped in green leaves or packed inside a type of woody mushroom called tinder fungus that could catch a spark and smolder inside itself for hours. It was basically a biological lighter, and we know this wasn't just guesswork. When they found Otzi the Iceman, the 5,300-year-old frozen man preserved in the Alps, he was carrying a complete fire kit in his belt pouch. Tinder fungus, flint, iron pyite for striking sparks, and extra plant tinder as backup. Even 5,000 years ago, losing your fire was serious enough that people carried dedicated equipment to prevent it. So, when rain hit, the first priority wasn't shelter, it was the fire. Move it deeper into the cave, shield it with hides or brush, feed it carefully. Not too much, not too little. Find dead lower branches from coniferous trees, the ones still protected by the canopy above, usually still dry underneath. Split open wet logs to get at the dry wood inside. Use birch bark as kindling, because birch contains a chemical called betulin that actually burns even when it's wet. One person's entire job during a rainstorm might have been just sitting next to that fire for hours, feeding it, shielding it, making sure it didn't die because that fire was everything. It was warmth, light, safety, cooked food, and the center of every social interaction the group had. Letting it go out wasn't just careless, it was potentially fatal for everyone. All right, so the fire is going and you're mostly dry, but you cannot leave. So what do? You make things. The archaeological record is very clear on this. Caves and rock shelters are absolutely packed with evidence of manufacturing. Stone tools in every stage of production, piles of flaking debris, those tiny chips of rock that fly off when you're shaping a tool found concentrated in specific spots inside caves. Exactly where someone would sit near firelight and work for hours. But it wasn't just stone tools. At Blombo's cave in South Africa, archaeologists found a 100,000-year-old ochre processing workshop. Abalone shells used as mixing bowls. Ochre ground into powder. Bone tools used to stir and apply it. This wasn't basic survival. This was production. Someone sat in that cave probably while the rain pounded outside and manufactured pigment on purpose with a system. And then you've got bone needles. They start appearing in the record around 61,000 years ago in South Africa and later across Europe and Asia. These are delicate, precise tools with tiny drilled eyes. You don't make a bone needle while you're running from something. You make it when you're sitting still, focused with hours to spare. Rainy days gave people that time. Now, here's where it gets really interesting. At a Neanderthal site called Abri du Maras in France, archaeologists found a tiny fragment of twisted plant fiber string dating to roughly 5,200 years ago. That's the oldest direct evidence of string ever found. And then at Hohlefels Cave in Germany, they discovered a 35,000-year-old tool carved from mammoth ivory with 4 holes and spiral grooves designed specifically for twisting plant fibers into rope. Someone sat in that cave and carved a dedicated rope-making machine. Making rope is slow, repetitive, and requires patience. It's the perfect bad weather task, and rope changed everything. It let you tie things together, build better shelters, create snares and traps, bind tools to handles. An incredible amount of human technology runs on string. And string was almost certainly invented by someone stuck inside waiting for rain to stop. And it wasn't just tools and rope, people were also making their shelters livable. At Sibidu Cave in South Africa, archaeologists found something most people wouldn't expect from 77,000 years ago. Bedding, actual bedding. Layers of sedges, rushes, and grasses carefully arranged as sleeping mats. The top layers included leaves from a plant called Cape Laurel, which is a natural insect repellent. Someone wasn't just surviving in that cave. They were making it comfortable, they were making it home, and the bedding was periodically burned and replaced to keep it clean. 77,000 years ago, people were already doing pest control. But here's where the story takes a turn that nobody expects. Because all of that, the tools, the rope, the bedding, that's the practical stuff. What came next is something else entirely. The art. The Chauvet Cave in southern France contains paintings that are roughly 36,000 years old. Lions, horses, rhinos, bears, drawn with a level of skill and observation that still shocks people today. The artists understood anatomy, movement, perspective. Some of the animals are drawn mid-stride, muscles tensed, heads turning. These aren't doodles. These are the work of people who watched these animals for thousands of hours and then recreated them from memory deep underground by firelight. And Chauvet isn't alone. Lascaux, Altamira, Sulawesi, and Indonesia, where cave art dates to at least 45,000 years ago, making it the oldest known figurative art in the world. But here's what makes this really interesting. These paintings aren't at the entrance of the cave where you'd sit for shelter. They're deep, sometimes hundreds of meters in through narrow passages and chambers you'd have to crawl to reach. Someone carried animal fat lamps into total darkness and painted. And think about that for a second. Nobody does that when the weather's perfect and the hunting's good. You do that when you can't go outside. When the rain has been falling for 2 days and you've already sharpened every tool you own and there's nothing left to do but go deeper into the dark and create something. Now, we can't prove that cave art was a rainy day activity, but the logic holds together. The most creative explosion in human prehistory happened in the exact places where people were most likely to be stuck inside for extended periods. And that leads to something even bigger. Rain didn't just create art, it might have created culture itself. Think about it. What happens when 15 to 30 people are forced into a confined space together for days with nothing to do? You talk, you listen, you share information. In 2014, anthropologist Polly Weisner published a study where she compared daytime conversations and nighttime fireside conversations among the Yuhuansi Bushmen in the Kalahari Desert. During the day, people talked about practical things, land rights, resources, complaints. But at night, around the fire, over 80% of the conversation shifted to stories, songs, and ceremonies. The firelight changed what people talked about. It softened faces, reduced tension, created a space where people opened up. The campfire wasn't just warmth, it was the original social network. And the stuff being shared around that fire wasn't small talk, it was survival. Where the water sources dry up in summer, which plants are safe to eat. Where the best flint deposits are, how to track a specific animal. That's not gossip. That's critical knowledge being passed from one brain to another through speech. And then beyond the practical stuff, there was something else. Stories, myths, explanations for why the rain comes and where it goes. Every ancient culture on Earth has rain mythology, and someone invented those stories. They almost certainly did it while sitting in the exact situation the story was trying to explain. And here's something that shows just how powerful this storytelling actually was. The oldest known oral traditions that have been verified against real geological events are Australian Aboriginal stories describing sea level changes that happened roughly 7,000 years ago. Those stories survived for 7,000 years through nothing but people telling them to each other. That kind of cultural memory doesn't develop unless groups spend enormous amounts of time doing exactly that. Sitting together, retelling stories over and over and over again. So rainy days weren't dead time, they were transmission time. The days when knowledge moved from the old to the young. When skills were taught by demonstration, when the group's collective memory got reinforced and updated. Now, here's the part nobody talks about. Rain wasn't always bad. Sometimes it was actually the best thing that could happen. After a heavy rain, the ground is soft, and soft ground means perfect tracks, deep, clear, detailed. You can see exactly which animals walked past, how long ago, how fast they were moving, and where they went. Some of the best tracking conditions in the world come right after rain stops. Rain also meant water. Humans could collect and store rainwater, and even early hominins may have understood this. Rock depressions that fill with clean water during rain are found near almost every known prehistoric campsite, and some of them show signs of being deliberately carved deeper to hold more. But water wasn't the only thing rain brought. Mushrooms and certain plants explode after rain. Tubers are easier to dig from wet soil. Insects come to the surface. A rainy period didn't stop the food supply. It changed it completely, and the groups that understood those changes had an enormous advantage over those that didn't. Termites are a perfect example. They swarm after rain in tropical Africa. They're one of the most protein-dense foods available. You don't need tools, you don't need weapons, you just pick them up. There are chimpanzees today that gorge on termite swarms after rainstorms. Early humans almost certainly did the same thing, probably on a much larger scale. So, what did ancient humans do when it rained all day? Everything that mattered. They kept the fire alive. They made the tools they'd use for the next hunt. They sewed the clothing that would keep them warm through winter. They twisted the rope that would hold their shelters together. They ground the pigment they'd use to paint animals on cave walls deep underground. They told the stories that would carry survival knowledge across generations. And when the rain finally stopped, they walked outside into soft ground, covered in perfect animal tracks, and got back to work. Rain didn't slow them down. It gave them time to prepare for everything that came next. Every tool, every piece of clothing, every story, every painting on a cave wall, all of it came from downtime. From the hours and days when they couldn't go out and had nothing to do except sit near a fire and think. Boredom didn't exist for them the way it does for you. Because when you're sitting in a cave with the rain hammering outside and your survival depends on what you make with your hands in the next few hours, you don't get bored. You get creative. And that might be the single biggest reason we're still